Towering over landscapes, these colossal structures defy engineering limits and challenge the laws of physics. From gravity-defying bridges to ocean-spanning tunnels, each project pushed technology and human ingenuity to the brink. Today, we uncover the hidden challenges, daring innovations, and extraordinary risk behind mega projects that shouldn't exist.
The Australia Pacific LNG project is one of the largest and most complex energy projects in the world. Located in Queensland, Australia, this project involves the extraction, processing, and transportation of natural gas from coal seams in the Surat and Bowen basins. The gas is then converted into liquefied natural gas for export to international markets. The project includes three main components: the gas fields, a 530-kilometer gas pipeline, and an LNG processing and export facility on Curtis Island. The construction of the gas fields involves drilling thousands of wells and installing extensive networks of gathering lines and processing facilities. These wells are drilled using advanced drilling techniques to reach deep coal seams and extract the gas. Hydraulic fracturing, or fracking, is employed to enhance gas flow, requiring precise control and monitoring to ensure environmental safety. The 530-kilometer gas pipeline is a critical component, transporting gas from the fields to the LNG facility. Constructing this pipeline involves trenching, welding, and laying pipes across diverse terrains, including forests, rivers, and farmland. Engineers use horizontal directional drilling to install the pipeline beneath major obstacles without disturbing the surface. This technique is particularly useful for crossing rivers and environmentally sensitive areas. The LNG processing facility on Curtis Island is where the gas is cooled to -260 degrees Fahrenheit, transforming it into a liquid state for easier transport. This facility comprises liquefaction trains, storage tanks, and loading jetties. Each liquefaction train often involves complex engineering, with compressors, heat exchangers, and cryogenic piping systems working together to cool and liquefy the gas. The storage tanks are massive, double-walled structures designed to safely store the LNG at extremely low temperatures. One of the significant challenges of the Australia Pacific LNG project is the integration of its various components into a cohesive system. This requires meticulous planning, coordination, and execution to ensure all parts work seamlessly together. Additionally, the project must adhere to strict environmental and safety regulations, necessitating advanced monitoring and control systems to minimize environmental impact and ensure the safety of workers and surrounding communities. Moreover, the logistics of transporting such large volumes of natural gas require sophisticated shipping and handling facilities. The LNG is loaded into specially designed carriers equipped with advanced containment systems to prevent the leakage and ensure safety during transit. These carriers transport the LNG to international markets where it's regasified and distributed through local gas networks.
Next on our list is the remarkable Salton Sea Restoration Project. This project is not only huge in scale, but also critical for the environment and public health. Once a popular tourist destination, the Salton Sea has now become one of the most polluted bodies of water in the country, with dust storms spreading toxic chemicals into nearby communities. The Salton Sea Restoration Project is part of the 10-year Salton Sea Management Program. The $400 million restoration plan includes reducing harmful dust and creating sustainable habitats. The first phase of this project is still underway, primarily focusing on restoring wildlife habitats, stabilizing air quality, and mitigating the effects of the receding waters in the sea. Let's talk about some of the engineering marvels and techniques being used. One of the most critical components is the Species Conservation Habitat Project, which broke ground in 2021. This project will restore approximately 4,100 acres of shallow water habitats that have been lost due to rising salinity in the sea. By reintroducing shallow water environments, the project aims to protect fish and bird populations, especially those on the Pacific Flyway. The North Lake Project is another ambitious project within the SSMP. By restoring 1,600 acres of aquatic habitat, this project will benefit local biodiversity and water quality. The North Lake Pilot Demonstration Project is already in development, acting as a testing ground for the full-scale restoration. Next, we'll see vast stretches of land once barren, now covered in lush vegetation. Native plants like cattails and bulrushes are being used to stabilize exposed areas of the lake bed. These plants help to anchor the soil, reducing the risk of wind-blown dust that carries toxic particles in the air. Restoring vegetation along the shoreline doesn't just improve air quality, it creates new habitats for local wildlife. The restoration doesn't stop there. Projects like the Desert Shores Channel Restoration aims to refill boat channels that were once popular in the Desert Shores Marina. By reintroducing water into these channels, the project supports both local recreation and environmental health. The Audubon Bombay Beach Wetland Enhancement Project is another exciting initiative, focusing on restoring 832 acres of vital wetland habitat. This project will benefit countless migratory birds and fish, making the Salton Sea a haven for wildlife. The federal government has committed $175 million for the Inflation Reduction Act to accelerate restoration efforts. This complements over $500 million in state funding, providing a significant boost to the ongoing projects. One of the main goals is to address air quality issues caused by the shrinking sea by creating a network of ponds and wetlands designed to support wildlife and reduce dust emissions. The restoration plan isn't just about improving the environment, it's a lifeline for the local community. It's super exciting to see such a large-scale project effort dedicated to restoring a natural treasure while protecting public health.
Giga Berlin is Tesla's first European gigafactory, located in Brandenburg, Germany. This massive facility is designed to produce electric vehicles and batteries, significantly expanding Tesla's production capacity. The construction of Giga Berlin involves extensive site preparation, building construction, and the installation of advanced manufacturing equipment. Site preparation includes clearing and leveling the land, as well as installing utility infrastructure such as water, electricity, and sewage systems. This process requires careful planning and execution to ensure the site is ready for construction. The main buildings of Giga Berlin are constructed using prefabricated steel frames and panels, allowing for rapid assembly and scalability. These buildings include production lines, assembly areas, and administrative offices. The construction process involves extensive coordination between various contractors and suppliers to ensure all components are delivered and installed on time. One of the significant challenges of Giga Berlin is the installation of advanced manufacturing equipment. This equipment includes robotic assembly lines, battery production machines, and quality control systems. Installing and calibrating this equipment requires precision engineering and technical expertise to ensure optimal performance. Additionally, Giga Berlin incorporates numerous sustainability features, such as solar panels, rainwater harvesting systems, and energy-efficient HVAC systems. These elements reduce the facility's environmental impact and align with Tesla's commitment to sustainability. The construction also involves extensive collaboration with local authorities and communities to address concerns and ensure compliance with regulations.
Nestled in the breathtaking Himalayas, Bhutan faces a unique challenge: the ever-growing risk of glacial lake outburst floods. These catastrophic events occur when glacial lakes, fed by melting ice, burst their natural dams, sending torrents of water crashing down the valleys. To mitigate this looming threat, Bhutan undertook the Thormy Lake Diversion Project, a bold initiative to reduce the water level of the rapidly expanding Thormy Lake and protect the downstream communities. Imagine standing at over 4,400 meters above sea level, surrounded by towering peaks and breathtaking landscapes, and knowing that a hidden danger lurks beneath all that beauty. That's the reality of Thormy Lake in Bhutan. It's one of many glacial lakes in the region, fed by glaciers that have been melting at an alarming rate. Why? Climate change. The rising global temperatures have caused these glaciers to retreat faster than ever, and as they melt, the water collects in lakes like Thormy, swelling them to dangerous levels. Here's where it gets scary. The lake is held back by a natural moraine dam, a wall of rock and debris left behind by retreating glaciers. It's like a fragile plug holding back millions of cubic meters of water. If that dam were to fail, the resulting flood could sweep through villages, destroy farmland, and wipe out critical infrastructure downstream. The destruction would be catastrophic for a country like Bhutan, where people live in harmony with nature but are now facing the harsh realities of a warming planet. So, what did Bhutan do? Did they call in heavy machinery, helicopters, or fancy high-tech solutions? Nope. Instead, they turned to something far more inspiring: human ingenuity, grit, and old-school hard work. Back in 2009, the Thormy Lake Diversion Project was launched with a simple but ambitious goal: lower the lake's water level to reduce the risk of a devastating flood. But here's the catch. Bhutan's rugged, remote terrain made it nearly impossible to bring in heavy equipment. Imagine trying to haul excavators or cranes up narrow, winding mountain paths. It just wasn't going to happen. So, they did it the old-fashioned way. Workers, including local villagers, trekked to the site on foot. That's right, at over 4,400 meters above sea level, in freezing cold and oxygen-thin air, they climbed to the glacial lake armed with little more than basic tools and sheer determination. Their mission? To dig controlled channels that would gradually release water from the lake, lowering its level in a safe, manageable way. Think about that for a second. This wasn't just some casual digging. We're talking about extreme manual labor at altitudes where most people struggle just to breathe. The weather was brutal, ranging from icy winds to sudden snowstorms. Yet, these workers pressed on, chipping away at the moraine dam, stabilizing it bit by bit, and carving out channels by hand. It's the kind of effort that makes you stop and marvel at what humans can achieve when faced with a challenge. What's even more remarkable is how this project blended traditional methods with modern environmental goals. In a world where we often look to technology for every solution, Bhutan showed us that sometimes simpler, human-powered approaches can be just as effective and more sustainable. Sure, it took longer and required an extraordinary amount of physical effort, but it worked. The lake's water level was lowered, the dam was stabilized, and the immediate threat of a catastrophic flood was significantly reduced. But the story doesn't end there. This project wasn't just about protecting people and land. It was also a powerful example of how a small nation like Bhutan is stepping up to tackle the global climate crisis. Bhutan, after all, is known for its deep respect for nature and its commitment to environmental preservation. They're a carbon-negative country, meaning they absorb more carbon dioxide than they emit. Yet, they're on the front lines of climate change, dealing with problems they didn't create. But we have to talk about the Hampton Roads Bridge Tunnel Expansion, one of the largest transportation infrastructure projects in the United States. This massive undertaking aims to alleviate congestion, improve travel times, and enhance connectivity between Norfolk and Hampton in Virginia. With an estimated budget of $3.8 billion, the project is one of the most expensive highway expansions in the country. The original Hampton Roads Bridge Tunnel, which opened in 1957, was the first bridge tunnel in the world. Designed to accommodate increasing traffic between Norfolk and Hampton, it became a vital corridor for commerce and military transport. A second tunnel was added in 1976, doubling its capacity, but by the early 2000s, traffic volumes had far exceeded its design limits. Over 100,000 vehicles crossed the HRBT every day, leading to severe congestion during peak hours. To address this, the Virginia Department of Transportation proposed a massive expansion project approved in 2016. This project is critical as Hampton Roads is home to Naval Station Norfolk, the largest naval base in the world, and several other military installations. The HRBT expansion will widen the I-64 corridor from 4 lanes to 8 lanes, doubling the current road capacity. The most technically challenging part of the project is the construction of 2 new parallel tunnels, each over 1.5 miles long, using tunnel boring machine technology. These tunnels will be the first bored tunnels in the Hampton Roads region, replacing the outdated immersed tube method used in the existing tunnels. The new tunnels will be designed to withstand extreme weather conditions, including hurricanes and flooding, making the corridor more resilient to climate change. The expansion will also upgrade existing bridges, roadways, and interchanges, improving traffic flow, safety, and overall efficiency. For the bridge expansions, floating cranes and barges are used to transport and install prefabricated sections. Crews are also employing GPS-guided excavation equipment and real-time monitoring systems to ensure precision in alignment and structural integrity. The $3.8 billion budget makes the HRBT expansion the largest transportation infrastructure investment in the history of Virginia. Currently, the project is more than halfway complete, with significant progress made on tunnel boring and roadway expansions. The TBM has completed over 50% of its excavation, and workers have started installing the final structural reinforcements inside the tunnels. The bridge widening is also progressing, with several new lanes already operational. The project remains on schedule for completion by 2027, with commuters and businesses eagerly anticipating the benefits. Once finished, the Hampton Roads Bridge Tunnel expansion will reduce congestion by up to 40%, cut travel times during peak hours, and provide a more efficient and safer route for travelers. Every aspect of the Gordie Howe International Bridge's construction showcases the intricate interplay between transnational coordination, advanced structural engineering, and logistical execution at a scale rarely attempted in modern infrastructure. Spanning the Detroit River and connecting Detroit, Michigan with Windsor, Ontario, this cable-stayed bridge is designed to support massive volumes of commercial and passenger traffic, requiring not only the longest main span of any cable-stayed bridge in North America, but also a level of precision in its execution that leaves no room for error. The construction began with extensive geotechnical investigations on both riverbanks. Drilling rigs bored deep into the soil and bedrock to analyze subsurface conditions, as the design called for massive pylon foundations to be embedded securely below the frost line and into competent strata capable of bearing immense vertical and lateral loads. These foundations were formed using deep caisson shafts, reinforced with high-density steel cages and tremie concrete placed underwater to displace slurry and avoid cold joints. Each tower foundation supports a pylon rising hundreds of feet above the river, built incrementally using a climbing formwork system that allowed for the continuous casting of reinforced concrete without the need for external scaffolding. The bridge deck, a post-tensioned concrete and steel composite structure, was constructed in segments using balanced cantilever methods. Each deck segment was either precast off-site and transported by barge or cast in place atop temporary platforms extending from the pylons. As the main span grew outward toward the center of the river, temporary stay cables were anchored into the pylons and attached to each newly added segment. These cables, arranged in a fan pattern, were tensioned precisely using hydraulic jacks to counteract gravitational sag and to distribute structural loads symmetrically across both sides of the pylon. The stay cables themselves consist of high-strength steel strands encased in corrosion-resistant sheathing, anchored into massive anchor blocks within the pylon shafts. Vibration dampers were installed at intervals to mitigate wind-induced oscillations and ensure long-term fatigue resistance. Behind the structural work, the installation of intelligent transportation systems, roadway lighting, drainage infrastructure, and barrier systems proceeded concurrently. A crucial aspect of the bridge's construction involved integrating border control and inspection facilities on both sides, meaning the project had to encompass not just the main span and approaches, but also expansive landside infrastructure. These included customs plazas, inspection booths, weigh-in motion sensors, and secondary screening areas, all built to exacting standards set by two national governments. Coordination across these parallel construction zones required synchronized project management, shared construction specifications, and harmonized safety and environmental protocols. Cross-border utility integration further complicated the process. Power, water, data, and fiber optic lines had to be laid in conduits embedded within the bridge deck, secured and protected against temperature fluctuations, dynamic load stress, and electromagnetic interference. Weather posed another challenge. Extreme temperature swings, high wind exposure during deck segment installation, and ice buildup along the river all required constant monitoring and adaptive construction scheduling. With a total length extending over a mile and traffic capacity tailored for future expansion, the Gordie Howe International Bridge is not simply a physical connection between two cities. It represents a structural embodiment of modern binational cooperation and the evolving science of long-span bridge engineering, where every bolt, cable, and foundation element plays a precise role in maintaining stability, durability, and flow across one of the continent's most critical commercial corridors. Set amid the subtropical lowlands of Central Florida, the construction of the Walt Disney World Resort in Orlando represented a pioneering feat of engineering, site development, and logistics management on an unprecedented scale. Spanning over 40 square miles, the transformation of this expansive and largely undeveloped land into a fully functional entertainment and hospitality complex required not only creative vision, but also advanced technical planning across multiple disciplines, including civil engineering, structural systems, utilities, transportation, and geotechnical stabilization. The first major task undertaken was the extensive site preparation, as much of the land was composed of wetlands, swamplands, and pine flatwoods with limited load-bearing capacity. To make the site suitable for large-scale construction, engineers employed a vast drainage and land reclamation strategy. A series of canals, retention basins, and stormwater management systems were excavated to control the water table and direct excess runoff into purpose-built bodies like Bay Lake and the Seven Seas Lagoon. This required dredging operations, the installation of culverts, and the construction of pump stations to regulate flow in both flood and drought conditions. Foundational work across the resort faced challenges due to the high water table and soft underlying soils. To ensure structural stability, deep foundations such as driven concrete piles and auger cast piles were commonly used, especially beneath heavy buildings like resort hotels and amusement park infrastructure. For lighter structures, engineers used preloading and surcharging techniques to compact the subgrade. In certain areas, soil cement stabilization and geotextile reinforcement were added to increase load distribution and prevent long-term settlement. Perhaps the most iconic aspect of the site's infrastructure was the creation of the so-called utilidor system beneath the Magic Kingdom. Rather than being true underground tunnels, these service corridors were constructed at the original ground level. The rest of the park was then built atop a massive earthen berm created by the spoil from the lagoon dredging. These utilidors house all the park's essential support systems, including electrical cabling, water distribution lines, HVAC systems, waste disposal, and logistics corridors, allowing for seamless and invisible operations above. Utility infrastructure was designed with redundancy and scale in mind. Independent water treatment and wastewater facilities were constructed on-site to handle the large demand. Extensive power distribution networks, including multiple substations, were integrated into the landscape to provide uninterrupted electrical supply across the property. Chilled water systems were installed to provide air conditioning via underground piping loops, using centralized plants that optimize energy efficiency. Transportation planning also played a critical role. A multimodal network was engineered to facilitate the movement of guests and goods, including monorail lines, ferryboat systems, internal bus loops, and service roadways. The monorail system, composed of elevated precast concrete beams supported by reinforced concrete piers, was built with precise tolerances to ensure smooth travel and high passenger throughput. All stations and transfer points were constructed with ADA, compliance and capacity planning in mind, utilizing modular concrete platforms, steel framing, and covered walkways. The scale and complexity of building the Walt Disney World Resort in Orlando set new benchmarks for themed development and remains a masterclass in how multidisciplinary engineering can be applied to create not just buildings or rides, but an entire controlled and immersive built environment engineered to handle millions of visitors each year with both efficiency and spectacle.
Sao Paulo Metro Line 4 in Brazil is a critical infrastructure project designed to improve public transportation in the world's largest cities. The new metro line spans over 12 kilometers and includes 11 stations. The construction of Line 4 involves advanced tunneling techniques, station construction, and installation of modern train control systems. Tunneling for the new line employs tunnel boring machines to excavate and install tunnel segments simultaneously. This method ensures the tunnels are structurally sound and minimize disruptions to the surface. The tunnels are lined with precast concrete segments, providing a durable and waterproof structure. The construction of stations involves creating large underground spaces capable of accommodating thousands of passengers daily. Each station is designed with multiple levels, including concourses, platforms, and service areas. The construction process includes extensive excavation, concrete pouring, and steel reinforcement to create durable, safe, and accessible stations. The installation of modern train control systems is essential for the efficient operation of Line 4. These systems include automated train operation tech, which allows for driverless train operation, improving efficiency and reducing the risk of human error. The ATO system is integrated with an advanced signaling and communication system, ensuring smooth and safe train movements throughout the network. One of the significant challenges of the Sao Paulo Metro Line 4 project is managing construction in a densely populated urban environment. Engineers must carefully plan and execute construction activities to minimize disruptions to daily life and ensure the safety of workers and residents. Additionally, the project must adhere to strict environmental and safety regulations, requiring advanced monitoring and control systems to mitigate impacts. Furthermore, the project includes the development of comprehensive support infrastructure, such as maintenance depots and control centers, to ensure the long-term operation and maintenance of the metro system. These facilities are equipped with advanced diagnostic and maintenance tools to ensure the reliability and safety of the trains and infrastructure.
The Echo Water Project in Sacramento is a massive undertaking, and it's making waves, literally. With a budget of $1.7 billion, this project is transforming how California manages its water amid a historic drought. California is no stranger to water crises. The recent years have only intensified the challenges. In 2022 alone, California recorded one of its driest years ever, forcing more than 600 square miles of farmland to be left fallow due to the insufficient water supply. But with the completion of the Echo Water Project, there's hope on the horizon. The Biological Nutrient Removal Facility is the crown jewel of the Echo Water Project. The BNR facility consists of 8 massive basins filled with specialized tubes that release oxygen into the wastewater. This process supports the growth of bacteria, which in turn removes 99% of ammonia and 89% of nitrogen from the water. These harmful chemicals are responsible for polluting waterways and contributing to environmental degradation. With the BNR facility in place, the treated water is much cleaner and safer to release into the environment. The project also includes a network of tertiary treatment facilities, where the water undergoes further filtration and disinfection. These facilities are a marvel of modern engineering, constructed with over 40,000 tons of steel and 170,000 cubic meters of concrete. These giant concrete structures, pumping stations, and electrical installations work together to ensure the highest level of water treatment. The digital twin of the entire facility was used during the construction phase. This digital twin is a virtual replica of the wastewater treatment plant, allowing engineers, contractors, and designers to visualize and manage every aspect of the construction process in real time. Jeff Campbell, director of virtual planning, explained, "We had a very strict concrete pour requirement of this project, so we really couldn't afford a lot of leaks." This project broke ground in 2015 and took 7 years to complete. With construction finishing in 2022, managing such a large project was no easy task. especially since the wastewater treatment plant had to remain operational throughout the entire process. With 22 individual projects running simultaneously, the complexity of the build was immense, but thanks to digital twin technology, the project was completed without major delays, and even came in $400 million under budget. Now that the Echo Water project is operational, it's not just about cleaning wastewater, it's about putting that water to good use. By 2025, the project will be a crucial component in agricultural reuse and sustainable farming efforts in southern Sacramento County. A new pump station and pipelines will direct to treated water from the plant to agricultural land. This will reduce the need for groundwater pumping, allowing aquifers to recover. Up to 16,000 acres of farmland will be irrigated with this reclaimed water. This offers a sustainable solution for agriculture, which has been devastated by years of drought and falling crop revenues. The Echo Water project is a blueprint for the future that'll help California manage its water crisis head-on. With the ability to treat and reuse millions of gallons of water every day, the Echo Water project is not just helping today, it's preparing California for tomorrow.
Saudi Arabia, as you probably know, is a country that's heavily dependent on oil and has next to no natural freshwater resources. They're basically sitting on a desert where it rarely rains, and yet they've managed to come up with a plan to reshape their future. The Artificial River project is ambitious, futuristic, and honestly kind of insane in the best way possible. When it's finished, it will span an unbelievable 12,000 kilometers, making it the longest man-made waterway on the planet. Let that sink in. 12,000 kilometers. That's about the same distance as traveling from New York to Sydney. But here's the kicker. This isn't your ordinary river. There's no flowing water you can see or boats cruising on its surface. It's an underground marvel, an intricate system of pipelines designed to transform seawater into freshwater using cutting-edge desalination technology. They're literally taking water from the ocean, removing the salt, and turning it into something drinkable and usable for farming. How cool is that? And it doesn't stop there. This freshwater is then transported through an insanely advanced network of pipelines that are specially built to resist corrosion. Some of these pipes are so big and deep, they make even the Nile look small in comparison. It's not just about water though, it's about reshaping the entire future of the country. Saudi Arabia is betting big on this project because they know they can't rely on oil forever. Oil runs out, but water is life. And by creating this artificial river, they're not only securing a reliable source of water for their people, but they're also revolutionizing agriculture in the desert. Imagine lush green fields and farms thriving in a place that was once bone dry. It's like turning a dream into reality. What's even more fascinating is the level of engineering and technology involved. I mean, we're talking about massive desalination plants that work around the clock, pipelines that stretch further than most people will ever travel in their lifetime, and a vision that's so audacious, it feels impossible until you see it happening. And they're not cutting corners either. This is about creating something sustainable and efficient, a solution that could inspire other desert nations facing similar problems. It's kind of wild to think about, isn't it? A project of this scale is no small feat. It takes years of planning, billions of dollars, and the collective efforts of some of the brightest minds on the planet. But when you think about the stakes, providing water to a country with no natural sources and paving the way for a more sustainable future, it feels worth it. Saudi Arabia is proving that even in the face of seemingly impossible challenges, human ambition and innovation can rise to the occasion. The primary purpose of this artificial river is to achieve water independence. For decades, Saudi Arabia has relied on desalination plants and ancient underground aquifers to meet its water needs. While effective, these methods have their limits. The aquifers are being depleted, and desalination is energy intensive. The artificial river aims to solve these issues by creating a sustainable and efficient way to supply water across the country. Imagine a future where every corner of Saudi Arabia, even the most remote desert areas, has access to a reliable water supply. But the vision doesn't stop there. The artificial river is also a cornerstone of Saudi Arabia's plan to revolutionize agriculture. By turning barren deserts into fertile farmland, the country hopes to reduce its reliance on food imports and diversify its economy beyond oil. Picture vast fields of crops growing where there was once only sand, powered by a river that flows beneath the surface. It's a transformative idea that could change how we think about agriculture in arid regions. The technology driving this project is nothing short of cutting edge. The desalination process involves two main methods: membrane filtration, where seawater is forced through ultrafine filters to remove salt, and thermal distillation, which involves heating seawater until it evaporates and then condensing it back into fresh water. Both methods are highly efficient, and the water produced is transported through pipelines with specialized anti-corrosion coatings to withstand the harsh desert environment. This ensures that the system remains operational for decades to come. The potential impact of this project is enormous. Beyond providing water, it represents a shift in how countries tackle resource scarcity. If successful, the artificial river could serve as a blueprint for other nations facing similar challenges. Let's move over to the Texas LNG Project, one of the most crucial energy developments in the United States, transforming the Gulf Coast into a powerhouse for LNG exports. Located in Brownsville, Texas, this $3.5 billion mega project is designed to process and export natural gas to international markets. The history of the Texas LNG project is tied to the growing role of the United States as an LNG exporter. The project was first conceptualized in the early 2010s when companies recognized the need for additional LNG terminals to keep up with rising global demand. By 2016, Texas LNG received initial regulatory approvals, and after years of planning, development officially broke ground in 2022. The site, situated near the port of Brownsville, was selected due to its proximity to key pipelines and access to deepwater shipping routes. This massive facility is being built to process, liquefy, and export LNG to key markets in Europe, Asia, and Latin America. It will take natural gas from major United States shale fields, cool it to extremely low temperatures, and convert it into liquid form for easy transportation via tankers. The facility includes one of the largest LNG storage tanks in the US, high-efficiency liquefaction units, and a sophisticated carbon capture system to minimize environmental impact. To transport gas to the plant, the project involves constructing over 200 miles of pipeline infrastructure, ensuring a constant and efficient supply from gas fields to the export terminal. The engineering and construction of the Texas LNG project require cutting-edge technology and heavy industrial equipment. The liquefaction process demands highly specialized machinery, including cryogenic heat exchangers and refrigerant compressors, capable of cooling natural gas to minus 162 degrees Celsius. Massive storage tanks with reinforced containment structures are being constructed to hold the liquefied gas before shipping. The terminal also includes loading arms and advanced docking systems, allowing LNG carriers to safely and efficiently receive cargo. Some of the largest LNG tankers in the world will dock here, carrying shipments to global destinations. Originally estimated at $2 billion, the total investment has now surpassed $3.5 billion, reflecting the complexity and scale of the project. The development is backed by major energy companies and investors, all betting on LNG as a key fuel source for the future. Currently, construction is nearing completion, with the first phase set to begin operations later this year. The Texas LNG project is expected to process and export over 4 million tons of LNG annually, significantly boosting United States energy exports. Towering above the Brickell skyline, The Panorama Tower in Miami represents one of the most ambitious high-rise construction efforts in Florida's history. With a height exceeding 800 feet, it stands as a benchmark in vertical development, blending residential, hospitality, office, and retail components into a single superstructure. Building such a skyscraper in a hurricane-prone, seismically inactive, but geotechnically complex coastal environment posed numerous engineering challenges that demanded both innovation and precision. Foundation work commenced with a comprehensive geotechnical survey to determine the capacity of the subsurface limestone bedrock typical of South Florida. The soil profile revealed layers of sand, silt, and coral rock, necessitating a deep foundation system capable of supporting the massive vertical and lateral loads. Engineers opted for a foundation composed of large diameter drilled shafts, some extending over 70 feet deep, socketed securely into the bedrock to prevent differential settlement. These shafts were reinforced with heavy steel rebar cages and filled with high-strength concrete, then capped with a massive mat foundation that was poured continuously over several days to ensure structural uniformity. The superstructure utilized a reinforced concrete frame system, chosen for its mass and resilience against wind loads, which are a critical design consideration for any structure of this height in a hurricane zone. The core of the tower, housing elevators, stairwells, and mechanical risers, was constructed using a slip-form system that allowed for continuous vertical progress. Surrounding the core, post-tension concrete slabs were used for the floor systems, providing high load capacity with reduced slab thickness, which helped to maximize ceiling heights within the constrained floor-to-floor space. Lateral stability of the tower was achieved through a combination of shear walls integrated into the core and strategically placed outriggers that tied the core to the perimeter columns at mechanical transfer levels. This configuration enhanced the tower's ability to resist overturning moments and sway, especially under hurricane-force winds. To monitor performance, embedded sensors were placed throughout the structure to track stress, strain, and movement in real time, feeding data into a centralized building management system. The tower's exterior envelope was composed of a curtain wall system featuring high-performance, hurricane-resistant glazing units with low-E coatings for energy efficiency. Each panel was factory assembled and tested for water infiltration, air leakage, and impact resistance before being hoisted into place. The facade was further reinforced at the corners and upper levels to account for increased wind pressures at higher altitudes. Mechanical, electrical, and plumbing systems were distributed across multiple levels with dedicated mechanical floors housing chillers, air handlers, backup generators, and electrical switchgear. These systems were installed with redundancy and flood protection in mind, given the potential for storm surge in the area. Chilled water loops and variable air volume systems ensured consistent climate control across the building's diverse spaces, from high-end residences to commercial offices. Vertical transportation was managed using high-speed elevators equipped with destination dispatch and regenerative drives to recapture energy during descent. Fire and life safety systems included pressurized stairwells, smoke evacuation systems, and multiple zones of sprinkler coverage to meet stringent code requirements for high-rise occupancy. From an engineering standpoint, Detroit Metropolitan Wayne County Airport is a layered composition of airfield systems, structural innovations, and transportation logistics brought together under one of the busiest aviation hubs in the Midwest. Its design and continual upgrades illustrate the demands of modern air travel on both infrastructure and operations, particularly in a four-season climate that presents snow, wind shear, and high summer heat. The layout of the airfield is dictated by a network of parallel and intersecting runways, each surfaced with high-strength Portland cement concrete capable of supporting repeated impact loads from wide-body aircraft. These runways are underlain with aggregate base courses and treated subgrades to mitigate frost heave and subsurface water migration. Embedded within each runway and taxiway are systems for runway lighting, electrical cable ducts, and aircraft guidance signs. Engineers incorporated FAA standard grooving on runway surfaces to improve water drainage and reduce hydroplaning risk, a critical detail in airport pavement construction. The terminals themselves are multi-story steel and concrete structures anchored by deep pile foundations. These piles extend below the frost line and into stable soil strata, designed to distribute vertical loads from the concourses and jet bridges. Each terminal is framed using steel columns and wide flange beams with composite concrete floor decks, chosen for their high strength-to-weight ratio and ability to span large open areas like ticketing halls and baggage claim areas. The roofs are framed with long-span steel trusses that allow for open, column-free spaces in the concourse areas, maximizing circulation and passenger flow. The McNamara Terminal, one of the key expansions at the airport, features an automated people mover system running the length of its concourse. The guideway was constructed with precast concrete guide beams mounted on cast-in-place piers, incorporating seismic joints and expansion bearings to accommodate thermal movement and vibration. The vehicles operate on a cable pull system embedded within the guideway, with control systems synchronized to station gates to optimize dwell times and passenger throughput. Beneath the passenger terminals lie extensive baggage handling systems, high-speed conveyors, diverters, and scanning units routed through multiple levels and security checkpoints. Mechanical engineers coordinated ductwork, fire suppression piping, and electrical conduit to share tight overhead spaces with baggage infrastructure, requiring three-dimensional coordination models and clash detection software during the design phase. Airside operations are supported by a fleet of underground utilities, including jet fuel hydrant systems, aircraft ground power units, and preconditioned air supply points. The hydrant fueling system was built with double-walled underground piping and leak detection monitoring, routed through trench boxes laid beneath the tarmac and connected to fuel farm distribution pumps at a remote site. Snow removal and de-icing are another critical infrastructure component. The airport includes heated pavement zones at gate positions, glycol collection systems with detention ponds, and airfield maintenance buildings equipped with vehicle staging, snowplow maintenance bays, and bulk material storage. Drainage systems are engineered to divert and treat de-icing fluids before discharge, ensuring compliance with environmental regulations. Next up, we have to talk about Kashagan Fields, nestled in the northern Caspian Sea near Atyrau, Kazakhstan. This mega project is a marvel of modern engineering and one of the most expensive and challenging oil projects ever undertaken. Discovered in 2000, it remains the largest oil discovery in the past 3 decades and the second largest globally, rivaling even the Tengiz field. This offshore oil reserve boasts recoverable reserves estimated at 13 billion barrels of crude oil, but its extraction has been fraught with technical, environmental, and economic challenges, culminating in a staggering development cost of $116 billion by 2012. The story of Kashagan begins in 1992, when Kazakhstan announced its intention to explore the resources of the Caspian Sea. A consortium of global energy giants began seismic surveys in 1997. By 2000, the vast potential of Kashagan was uncovered, sparking immense interest. However, the harsh environment posed immediate challenges, including extreme temperatures ranging from 35 degrees C to 40 degrees C, shallow waters, and high levels of hydrogen sulfide in the oil, making operations hazardous. The development of Kashagan demanded innovative engineering solutions. To navigate the shallow, ice-prone waters of the Caspian, artificial islands were constructed to house drilling rigs and production facilities. The primary operational hub, known as Island D, features cutting-edge technology for oil gas separation, sour gas reinjection, and dehydration. A 92-kilometer pipeline transports oil to onshore facilities. However, the initial pipeline failed due to corrosion from wet H2S, leading to its replacement with an Inconel-clad steel pipeline in 2016. The project also employed advanced drilling rigs, and ice-resistant platforms, while over 5,000 workers were engaged during peak construction phases. Living quarters were provided on floating barges, ensuring personnel safety and comfort amidst harsh conditions. The production began in 2013, though technical issues forced a halt soon after. Commercial production resumed in 2016, with an output of 370,000 barrels per day by 2017. By 2019, production had increased to 400,000 barrels per day, contributing significantly to the national economy, and positioning Kazakhstan as a vital player in the global energy market. The Kashagan Field has also been a focal point of geopolitical interest. In 2013, China secured an 8.4% stake in the project through its state-owned CNPC, emphasizing the strategic importance of the oil field.
Banten Port in Indonesia is a significant infrastructure project aimed at enhancing the country's maritime trade capacity. Located in West Java, the port includes a container terminal, car terminal, and supporting infrastructure. The construction of Banten Port involves a land reclamation, dredging, and construction of extensive port facilities. Land reclamation is the first step, involving the creation of new land by dredging and filling the seabed with sand and rock. This process requires precise engineering to ensure the reclaimed land is stable and suitable for construction. Engineers use advanced geotechnical techniques to compact and reinforce the soil, preventing subsidence and ensuring long-term stability. Dredging is essential for creating deep water channels and berths to accommodate large vessels. This involves removing sediment and rock from the seabed using specialized dredging equipment. The dredged material is carefully managed to minimize environmental impact, and in some cases, it is used for land reclamation. The construction of port facilities includes building quays, warehouses, and support infrastructure. The quays are constructed using reinforced concrete piles, driven deep into the seabed to provide a stable foundation. On top of these piles, concrete decks are cast to create the surface where cargo operations take place. Warehouses and other buildings are constructed using steel frames and prefabricated panels, allowing for rapid assembly and scalability. One of the significant challenges of the Banten Port project is managing the environmental impact of dredging and land reclamation. Engineers work closely with environmental experts to implement mitigation measures, such as creating artificial reefs and mangrove restoration projects to preserve marine habitats. Additionally, the project must adhere to strict safety and operational standards to ensure the ports can handle the anticipated increase in maritime traffic. Moreover, the integration of advanced port management systems is crucial for optimizing cargo handling and logistics. These systems include automated cranes, real-time tracking, and inventory management tools to ensure efficient and timely operations. The port's strategic location and state-of-the-art facilities are expected to enhance Indonesia's role in global trade.
Next on our list is the remarkable California high-speed rail. This project seeks to connect major cities across the state with a high-speed train system. It's currently projected to cost $135 billion. The rail system could connect cities like San Francisco and Los Angeles with trains traveling up to 220 miles per hour, reaching the journey between these two cities in under 3 hours. The first stretch of this high-speed rail is set to cover 171 miles across the Central Valley, from Merced to Bakersfield. This section is a critical part of the project and is targeted for completion by 2030. Once operational, it'll offer residents in the Central Valley a fast and efficient alternative to driving while laying the groundwork for further expansion. However, since its inception in 2008, the project has faced numerous setbacks. From the start, the cost and complexity of the project were underestimated. Early estimates suggested the project would cost around $33 billion, but over time, the budget ballooned to $135 billion. Despite these challenges, progress is being made. Construction is currently underway in the Central Valley, with several segments actively being built. This region was chosen for the first phase of construction because it's relatively flat, allowing for easier development compared to more challenging terrain of urban areas like Los Angeles or San Francisco. The high-speed rail promises to be a transformative force for California. but its success will depend on navigating the financial and logistical hurdles ahead.
It's time to look at Egypt's new Delta project. At the heart of this ambitious plan is a 170-kilometer artificial river, a man-made waterway designed to breathe life into one of the driest regions on Earth. For a country like Egypt, where the Nile River has always been the lifeline, this project is nothing short of revolutionary. By reducing dependence on the Nile, Egypt is not only addressing its own water scarcity, but also ensuring a more sustainable future. What makes this project truly innovative is how it sources its water. Unlike traditional irrigation systems that draw directly from rivers, the new Delta's artificial river uses treated wastewater and desalinated water. Think about that for a moment. Water that would otherwise go to waste is being recycled and repurposed to nourish crops and sustain communities. It's a clever and environmentally friendly solution that minimizes the strain on the Nile, which is already overburdened by a growing population and upstream demands. But the project doesn't stop there. It also includes emergency gates designed to manage potential Nile floods. This added feature acts like a safety valve, ready to absorb excess water during emergencies, ensuring that both the Nile and the new Delta system remain stable and functional. It's a smart way to tackle two problems at once: controlling floods and securing water for agriculture. The benefits of the new Delta project are nothing short of transformational. First and foremost, it's expected to significantly boost Egypt's food production. Picture a desert that once seemed inhospitable, now teeming with wheat, vegetables, and fruits. This increased agricultural output won't just feed Egypt's growing population, it will also reduce the country's reliance on food imports, saving billions of dollars and strengthening the economy. Beyond food production, the project is creating a ripple effect of opportunities. The development of this artificial river is accompanied by the construction of roads, power plants, and factories. These new facilities will create jobs, attract investments, and pave the way for the growth of entire communities in areas that were once uninhabitable. It's not just about growing crops, it's about building a future where people can thrive. Turning sand into farmland isn't something you see every day. It's the kind of vision that requires not just engineering expertise, but also a deep belief in the potential of human ingenuity. For centuries, the Nile was seen as Egypt's only source of life. The new Delta project flips that narrative on its head, proving that with innovation and determination, even the harshest landscapes can be transformed. Critics have pointed out the high energy consumption required for desalination and wastewater treatment. There's also the question of sustainability. How can Egypt ensure that this lush oasis remains viable in the long term? These are valid concerns, but the country is already taking steps to address them. By incorporating modern agricultural practices and carefully monitoring environmental impacts, Egypt is working to strike a balance between development and sustainability. Let's travel over to California, where Apple is once again pushing the boundaries of architecture. The Observatory, located within Apple Park in Cupertino, is a revolutionary space that combines innovation with design excellence. Set to become a major hub for research, product launches, and immersive experiences, the Observatory is the most ambitious construction project by Apple since 2017. The Observatory is built almost entirely underground, seamlessly blending with the surrounding landscape. With a stunning glass dome entrance, an open-air terrace with panoramic views, and cutting-edge materials, the structure is designed to inspire creativity and contemplation. Apple has long been known for its obsession with design. The headquarters, Apple Park, is often referred to as a spaceship due to its circular structure and futuristic aesthetics. However, Apple didn't stop there. It envisioned a space within Apple Park that would act as a masterpiece for innovation, where technology, architecture, and nature could coexist. The Observatory was conceived as a subterranean structure that would allow visitors to engage with nature while experiencing the latest technology by Apple. The design takes inspiration from ancient observatories and modern minimalism, using natural materials such as stone, terrazzo, and timber to create a space that feels both futuristic and organic. Unlike the flagship buildings of Apple, which are iconic for their futuristic, above-ground presence, the observatory is primarily built into the hillside. Visitors enter through a curved pathway that leads to a 3-meter wide oculus, a circular opening that allows natural light to flood the space. A sliding stone door leads into the main event hall, which features an open terrace with a portal-like window framing Apple Park and the mountains beyond. The observatory is powered entirely by on-site solar panels and wind energy, reducing its carbon footprint. The space is equipped with state-of-the-art augmented reality and artificial intelligence labs for testing next-gen Apple technology. Construction of the observatory began in 2020. Despite facing pandemic-related delays, Apple remained committed to delivering a space that embodied its vision of sustainability, creativity, and cutting-edge design. The observatory is a $3 billion project, making it one of the most expensive single-building investments by Apple. The construction team was led by Foster along with their partners, the same architectural firm that designed Apple Park and the Steve Jobs Theater. Their challenge was to create an entirely new type of space, one that felt open and airy despite being underground. Currently, the observatory is nearly complete, with final interior installations and landscaping in progress. The first public product launch is expected to take place in late 2025, marking a new chapter for event presentations by Apple. But next up, in tackling the extreme demands of spanning the Straits of Mackinac, a 5-mile-wide, windswept channel where Lake Michigan and Lake Huron converge, the Mackinac Bridge project stands as a masterclass in long-span suspension bridge engineering. Designed to accommodate seismic movement, thermal expansion, gale force winds, and ice flows, the bridge required a foundation to finish approach that pushed the boundaries of mid-20th century civil engineering. Work began with the placement of massive caissons in the deep strait. These caissons, steel cylinders reaching down to bedrock, were sunk using a combination of pneumatic excavation and underwater blasting. Once in place, they were backfilled with Thormy concrete to form the piers that would support the suspension towers. The towers themselves rise from these caissons and were assembled using high-tolerance riveted steel plates, lifted by derrick cranes mounted on temporary platforms. Due to the depth and water conditions, the foundation work took several seasons and required round-the-clock shifts with divers, dredgers, and engineers coordinating in tight, hazardous quarters. The twin suspension towers, over 500 feet tall, consist of welded steel box sections built segmentally. Each section was hoisted using cableways strung between temporary falsework and then precisely aligned and pinned. Once both towers reached full height, the construction team began spinning the main cables, a process that involved passing individual wires back and forth across the span using a spinning wheel, then compacting and binding the bundles into the final diameter. These cables were anchored into massive concrete anchor blocks at each end of the bridge, poured over bedrock and reinforced with thousands of tons of rebar to resist the horizontal forces imposed by the suspended roadway. With the main cable secured, vertical suspender cables were hung at set intervals and tensioned to support the weight of the roadway deck. The deck itself was constructed using steel trusses and orthotropic deck panels, lifted into place from barges using floating cranes and suspended from the cables using custom fabricated clamps. Expansion joints and rocker bearings were integrated into the deck structure to accommodate longitudinal movement caused by temperature variation and traffic loads. The bridge was designed to flex several feet in any direction, a dynamic capacity necessary to endure winter ice loads and summer thermal expansion. Wind tunnel testing and aerodynamic modeling informed the bridge's profile, which includes a narrow, open grid center lane section that reduces wind resistance and allows air to pass through the deck. Wind dampers and tuned mass dampers were also considered in the design to mitigate oscillations during high wind events. Paint systems for the structural steel involved multiple layers, including zinc-rich primers and elastomeric coatings designed to withstand harsh lake effect environments and freeze-thaw cycles. Maintenance access was engineered into the bridge with catwalks, internal tower ladders, and inspection rail trolleys integrated into the superstructure. De-icing and runoff control systems were also embedded into the deck, including scupper drains and weather monitoring sensors that inform bridge operation decisions. Stretching through the heart of Central Florida, the I-4 Ultimate project in Orlando represented a massive reconstruction and modernization of one of the state's most heavily traveled interstate corridors. The scale of this infrastructure initiative, spanning 21 miles, required an extraordinary application of highway engineering, traffic management, and structural design, all executed under live traffic conditions. The goal was not merely to widen the interstate, but to reconfigure it entirely to improve traffic flow, safety, and long-term capacity, incorporating express toll lanes, new interchanges, and updated overpasses. The initial phase of work focused on utility relocation and right-of-way clearing, including the removal of outdated bridges, underpasses, and surface roads. Utility coordination was especially complex given the corridor's urban setting. High-voltage transmission lines, water mains, gas pipelines, and fiber optic conduits were identified, surveyed, and in many cases rerouted through newly constructed utility corridors. Horizontal directional drilling and jack and bore methods were used extensively to install new conduits beneath active roadways without disrupting surface traffic. One of the hallmark features of the project was the addition of 4 managed express lanes in the center of the existing interstate. To construct these, engineers had to widen the footprint of the corridor and build new median support structures while maintaining the existing traffic lanes. This required extensive temporary shoring, phased traffic shifts, and the use of movable barrier systems. The new lanes were constructed with concrete pavement sections over a stabilized subbase and geotextile reinforced subgrade to support long-term heavy vehicle use. Bridges were a major component of the reconstruction effort, with over 100 new or rebuilt bridges included in the project scope. These ranged from short-span box girder structures to complex multi-level flyover ramps. Precast concrete beams were fabricated off-site and delivered during off-peak hours to minimize traffic disruption. Each bridge's foundation system was engineered to match local soil conditions, typically involving driven steel H-piles or drilled shafts. Bearing pads, expansion joints, and shear connectors were meticulously installed to ensure long-term durability and thermal movement capacity. The project's interchanges were completely redesigned to eliminate weaving and improve vehicular throughput. One of the most complex interchanges was the one at State Road 408, which required stacking multiple levels of traffic lanes, supported by tall piers and connected through sweeping curved ramps. Special seismic joints and post-tensioning systems were used in some of these long-span ramps to meet structural integrity standards and allow for maintenance access. Intelligent transportation systems were integrated throughout the corridor, including overhead gantries with dynamic message signs, cameras, and electronic toll collection systems. The express lanes were outfitted with barrier separation and entry-exit gates, spaced strategically to manage congestion. All ITS components were wired into a centralized traffic operations center, allowing for real-time monitoring and incident response. Let's travel over to Atlantis the Royal, located on the Palm Jumeirah in Dubai, United Arab Emirates. It is known for its opulent design, extravagant amenities, and stunning views of the Arabian Gulf. Adjacent to the iconic Atlantis, the Palm, this $1.2 billion masterpiece has transformed the city's skyline and established a new standard for hospitality and living. Conceived to expand the legacy of Atlantis, this project was designed as the epitome of luxury and sophistication. Construction began in 2016, spearheaded by globally renowned designers, architects, and engineers. The goal of this mega project was to merge timeless elegance with modern innovation, creating a space that would cater to ultra-luxury living and hospitality. Atlantis the Royal boasts 795 hotel rooms, 231 luxury apartments, and 90 swimming pools, including the spectacular Infinity Sky Pool, located 90 meters above ground. The architectural design combines bold, geometric forms with expansive glass facades, providing panoramic views of the Arabian Gulf and Dubai's skyline. A blend of cutting-edge technology and sustainable practices was integrated throughout, including energy-efficient systems and advanced construction materials. The project employed modular construction methods and state-of-the-art machinery, including tower cranes, precision cutting equipment, and advanced concreting techniques. The sky pool required a unique structural support system, enabling its seamless suspension at breathtaking heights. Additionally, the landscaping incorporates lush green spaces and water features, harmonizing with the surrounding environment. The residences at Atlantis, the Royal, offer 2 to 5 bedroom homes, meticulously designed to provide unparalleled living experiences. Townhouses feature private pools, landscaped gardens, and expansive entertainment areas, while penthouses boast breathtaking views, private terraces, and bespoke interiors. The sky courts elevate luxury further, with elevated terraces, dramatic pools, and panoramic views. Atlantis, the Royal, is home to 17 world-class restaurants, including 8 celebrity chef establishments, making it a culinary destination in its own right. Residents and guests enjoy access to private beaches, a state-of-the-art gym, a residents-only spa, and oceanfront leisure activities, including snorkeling and scuba diving.
Rail Baltica is a major infrastructure project aimed at integrating the Baltic states into the European rail network. This project involves constructing a new high-speed rail line connecting Estonia, Latvia, and Lithuania with Poland and the rest of Europe. The construction of Rail Baltica includes building new tracks, stations, and supporting infrastructure. Building the new tracks involves extensive earthworks, including excavation, grading, and laying ballast. The tracks are constructed using continuous welded rail, which provides a smoother and more reliable surface for high-speed trains. Engineers use advanced surveying and alignment techniques to ensure the tracks are straight and level, essential for maintaining high speeds and safety. The construction of stations and supporting infrastructure involves creating passenger facilities, platforms, and maintenance yards. These facilities are designed to be modern and accessible, providing a high level of comfort and convenience for passengers. Additionally, the project includes the installation of advanced signaling and communication systems to ensure safe and efficient train operations. One of the significant challenges of Rail Baltica is coordinating construction across multiple countries, each with its own regulations and standards. Engineers and planners must work closely with government authorities and stakeholders in each country to ensure the project meets all requirements and progresses smoothly. Furthermore, the project incorporates numerous sustainability features, such as energy-efficient systems, green infrastructure, and noise reduction measures. These elements reduce the environmental impact of the rail line and enhance the quality of life for communities along the route. The construction also involves extensive public consultation and engagement to address concerns and ensure transparency.
The California Water Fix, also known as the Delta Tunnels Project, is one of the most significant and controversial infrastructure projects in the history of California. This $17 billion plus proposal aims to modernize the water delivery system by constructing 3 massive underground tunnels in the Sacramento-San Joaquin Delta. There will also be 3 new water diversion facilities. These tunnels, each 35 miles long and 40 feet wide, are designed to protect water supplies for millions of residents in Southern California, Central Valley, and the Bay Area. The Delta is a critical water source, but it faces severe challenges due to environmental degradation, aging infrastructure, and the risk of earthquakes. This is a plan by Governor Jerry Brown to upgrade the state's aging water infrastructure and to move water in an environmentally friendly manner. The proposed tunnels will bypass the delicate ecosystem in the delta, diverting fresh water from the Sacramento River, enhancing water supply reliability, and aiding in delta ecosystem restoration. But there's massive controversy too. The project poses significant threats to endangered species like the delta smelt and the winter and spring-run Chinook salmon. Construction is expected to last over a decade. Once complete, the California water fix will provide reliable, clean, and secure water to almost 27 million Californians and 3 million acres of farmland. It'll improve environmental conditions in the Sacramento-San Joaquin Delta, alongside California Eco-Restore.
Let's travel over to the Seine Nord Europe Canal in France, a waterway so transformative, it's redefining how goods flow across Europe. With a hefty price tag of $5.5 billion, this 106-kilometer-long artificial river is one of the most ambitious infrastructure projects in Europe. It's designed to fix long-standing bottlenecks in the continent's inland waterways and set the stage for a future of seamless trade and economic prosperity. The existing network of waterways in this region, particularly the Canal du Nord, has long struggled to handle modern trade demands. The barges that currently navigate these waterways can carry a maximum of just 650 tons. That might sound like a lot, but in the world of shipping, it's not nearly enough to meet the growing demand for efficient cargo movement. The Seine Nord Europe Canal addresses this limitation by allowing much larger barges and push towers capable of carrying up to 4,400 tons to navigate its waters. It's like upgrading from a small delivery van to a massive freight truck, revolutionizing how goods are transported across France and beyond. The canal features 6 locks, each 54 meters wide and 4.5 meters deep. These locks aren't just there for show, they play a critical role in managing water levels and ensuring that boats can navigate the canal safely and efficiently, no matter the conditions. One of the standout features of this project is the aqueducts, particularly the one over the River Somme. This aqueduct is a staggering 1330 meters long and 25 meters high, making it a true feat of modern engineering. Picture this: a river of water suspended above another river, with boats cruising along as if they're gliding through the sky. There are also 2 additional aqueducts that cross major motorways, ensuring the canal integrates seamlessly with existing infrastructure. The benefits of the Seine Nord Europe Canal go far beyond its capacity to move goods. By connecting the Somme Basin to the Rhine Basin and integrating it into Europe's largest inland waterway network, the canal is set to handle an estimated 15 to 18 million tons of trade annually. This is a game changer for the region's economy, supporting industries, creating jobs, and fostering regional development. It's not just about trade though. The canal also acts as a source of drinking water and irrigation for nearby communities, ensuring its value extends to everyday life. With multimodal ports and recreational areas along its route, the canal is poised to attract visitors from around the world, turning what's primarily a commercial project into a hub for leisure and exploration. Let's discuss 1000M, a remarkable 73-story skyscraper rising in Chicago, designed by the legendary architect Helmut Jahn. This architectural masterpiece is redefining luxury living in the city, standing tall at 832 feet, making it one of the tallest residential buildings in Chicago. Located on 1000 South Michigan Avenue, this high-rise is reshaping the skyline with a futuristic glass facade that reflects the historical past and ambitious future of the city. The 1000M project was first announced in 2016 as a bold addition to the famous skyline of Chicago. The site, sitting near Grant Park, was carefully chosen to offer breathtaking views of Lake Michigan, making it a prime location for upscale residential living. The project was designed to cater to luxury homeowners and business executives, offering them a world-class urban living experience in the heart of the city. 1000M is designed to be more than just a high-rise. It is a self-contained luxury environment. Inside, the skyscraper houses a 3-story sky deck featuring a resort-style pool, a spa, and an observation lounge with panoramic views of Chicago and Lake Michigan. The residences are equipped with smart home technology, allowing residents to control lighting, climate, and security systems remotely. The exterior of the building is one of its most striking features. It consists of a futuristic glass curtain wall, engineered to reduce heat absorption while maximizing natural light. This energy-efficient design ensures that the building maintains comfortable temperatures while minimizing electricity consumption. The development also includes eco-friendly heating and cooling systems, making it one of the most sustainable luxury towers in the region. Originally, the estimated budget for 1000M was $470 million, but delays and supply chain issues caused the cost to rise. The project was stalled during the pandemic, as material shortages and financial uncertainties forced developers to pause construction. However, in 2022, the project was revived and construction resumed at full speed. The building required the use of massive hydraulic cranes to lift prefabricated steel beams and glass panels into place. Custom glass paneling machines were employed to ensure precision in the exterior facade installation. Engineers had to reinforce the foundation with deep concrete pilings, ensuring that the skyscraper could withstand the harsh winters and strong winds of Chicago. The first set of residents is expected to move in later this year, marking the completion of one of the most ambitious residential projects in Chicago. Seen from a systems integration perspective, the Q Line streetcar in Detroit represents a complex urban rail deployment that had to harmonize modern transit engineering with a dense, pre-existing streetscape. Unlike heavy rail or subway systems that benefit from dedicated rights-of-way, this streetcar line operates in mixed traffic along Woodward Avenue, requiring careful synchronization of vehicle operations, traffic signals, curbside access, and embedded infrastructure. The construction process began with extensive utility mapping and relocation. Since the corridor hosts decades of legacy infrastructure, gas, water, telecommunications, and electrical, the design-build team initiated ground-penetrating radar scans, potholing, and as-built analysis to identify conflicts. Where utility conflicts arose, crews executed trench excavations and coordinated shutoffs to reroute lines or deepen their burial beneath the projected slab track. These relocation efforts had to occur in tight time windows to avoid disrupting the urban core, with temporary road decking installed to maintain traffic flow during phased excavation. Track installation followed a slab track design, where continuous welded rail is embedded in reinforced concrete. To ensure vibration and noise isolation, each rail sits within elastomeric boots surrounded by flowable grout and high-strength concrete. This floating slab assembly reduces the transmission of mechanical vibration into adjacent structures and limits maintenance demands from thermal expansion and vehicle impact. Steel reinforcement within the slab was laid in grid patterns and connected to dowels anchored in expansion joints every several dozen feet, allowing for structural continuity while accommodating thermal cycling. Embedded in the track bed are induction loops for vehicle detection, signal actuation circuits, and grounding wires for stray current mitigation, especially critical given the electrified system. The Q Line uses an overhead catenary system to power its vehicles, which required the erection of catenary poles and the tensioning of contact wire at a precise height and stagger. These poles, founded in deep caissons drilled between underground utilities, also support street lighting and traffic signal heads in a combined pole design to reduce streetscape clutter. Station platforms were constructed at sidewalk level, but raised slightly to allow near-level boarding, with ADA-compliant ramps and tactile warning strips installed along platform edges. Each platform integrates real-time passenger information displays, emergency call boxes, and prefabricated canopies mounted on spread footings beneath the concrete platform surface. Coordinated with the signal control system, these stops are geo-fenced to allow priority requests at intersections, giving approaching streetcars limited signal preemption to maintain headways and schedule adherence. The vehicles themselves, housed in a dedicated maintenance and operations facility at the line's terminus, are bidirectional and equipped with low-floor designs. These articulated units include onboard diagnostics, regenerative braking systems, and GPS-based location tracking. The maintenance building was constructed with embedded track pits, overhead crane rails, and specialized lifts to allow undercarriage inspections and wheel truing operations. System commissioning involved several stages: overhead wire energization, vehicle clearance testing, dynamic braking trials, and integrated traffic signal tuning. All systems, including communications, fare validation, and emergency override functions, had to be stress tested before passenger operations commenced. Beneath the waters and roadways of Miami, the Port Miami Deep Dredge and Tunnel projects reshaped both the marine and terrestrial access to one of the busiest cargo and cruise ports in the United States. These two interconnected mega projects required cutting-edge marine engineering, precision tunneling beneath a densely populated urban core, and rigorous coordination between federal, state, and local agencies to expand the port's capacity and streamline its logistics network. The Deep Dredge project aimed to deepen the port's main shipping channel from 42 feet to 50 feet, allowing for the accommodation of new Panamax-class vessels transiting through the expanded Panama Canal. To execute this, specialized dredging vessels were brought in, including cutter suction dredgers and trailing suction hopper dredgers, capable of removing millions of cubic yards of seabed material. The challenge lay not only in excavating to such depths, but doing so without disrupting sensitive marine habitats, port operations, or submerged utilities. Dredging operations were sequenced in phases, beginning with hydrographic surveys to precisely map the underwater topography. Blasting was employed in sections of dense limestone, with marine-safe explosives timed to avoid impact to sea life. The excavated material was carefully monitored and disposed of at authorized ocean disposal sites or used in beneficial reuse programs like beach renourishment. Environmental control measures included turbidity curtains and marine species observers aboard all vessels. Simultaneously, the Port Miami Tunnel project unfolded beneath Biscayne Bay. This initiative involved the construction of twin tubes running approximately 4,000 feet in length, connecting the MacArthur Causeway on Watson Island to Dodge Island, the heart of the port. The tunnels were designed to divert truck traffic from downtown Miami, enhancing safety and easing congestion. To construct these tunnels, a custom-built tunnel boring machine, nicknamed Harriet, was deployed. Weighing over 2,000 tons and spanning nearly 40 feet in diameter, the TBM was assembled in a launch pit on Watson Island and advanced through a limestone substrate beneath the bay. The tunneling process involved simultaneous excavation and installation of precast concrete segment rings, forming the tunnel lining. These segments were waterproofed and grouted in place, forming a watertight shell that could withstand hydrostatic pressures and resist intrusion from saline water. Tunneling beneath the bay demanded constant monitoring of groundwater pressure, cut-ahead torque, and soil composition. The TBM operated with an earth pressure balance system to stabilize the tunnel face and prevent collapse. The spoil removed from the tunnel was conveyed by belt system to the launch shaft and trucked off-site. Crews worked in rotating shifts, operating around the clock to maintain excavation rates and minimize disruption to the bay and surrounding infrastructure. Once the structural shell was completed, interior systems were installed, including ventilation fans, LED lighting, fire suppression systems, CCTV surveillance, and emergency egress walkways. A robust stormwater drainage system was also built into the tunnel floor to channel any water intrusion into sump pits and eject it via high-capacity pumps. Taken together, the Port Miami deep dredge and tunnel projects not only increased the capacity and efficiency of port operations, but demonstrated how complex marine and tunneling engineering solutions can be successfully executed in a high-stakes, environmentally sensitive, and logistically intense urban setting. Let's discuss Plant Vogtle, a nuclear power plant located in Burke County, Georgia, in the United States. It is the largest nuclear power facility in the country, boasting a total capacity of 4,536 megawatts. Named after Alvin Vogtle, a former chairman of Alabama Power and Southern Company, the plant represents a blend of innovation, ambition, and engineering resilience. Plant Vogtle initially consisted of 2 Westinghouse pressurized water reactors, with Units 1 and 2 coming online in 1987 and 1989, respectively. These reactors were designed with General Electric steam turbines and electric generators, each offering a capacity of 1,215 megawatts. Their construction marked a significant investment jump from an estimated $660 million to $8.87 billion, a figure adjusted to $19 billion today. Despite these cost overruns, the Nuclear Regulatory Commission extended the licenses of both units to 2047 and 2049, ensuring their longevity. In 2009, plans to expand the plant with 2 additional reactors began, utilizing advanced Westinghouse AP1000 technology. These reactors incorporate passive safety systems and modular construction methods designed to improve efficiency and safety. Units 3 and 4 were equipped with nearly 600-foot-tall natural draft cooling towers, enhancing their cooling capabilities. However, the construction faced significant hurdles, including contractor delays, the 2017 bankruptcy of Westinghouse, and escalating costs. Originally budgeted at $14 billion, the project's costs ballooned to $34 billion by 2023. Unit 3 achieved commercial operations in July 2023, making it the first nuclear reactor in the US in 7 years. Unit 4 followed suit in April 2024, marking the completion of the ambitious expansion. The AP1000 reactors employed at Vogtle are cutting edge, featuring passive safety systems that can automatically cool the reactor core in emergencies without operator intervention. The cooling towers for these reactors are nearly 600 feet tall, making them among the tallest in the world. Advanced machinery like modular construction systems and robotic welding tools ensured precision but added complexity to the project. With the capacity to power over 1 million homes, it showcases the potential of nuclear power as a sustainable energy source.
The Mersey Gateway Bridge in the United Kingdom is a major infrastructure project designed to improve the connectivity and reduce congestion in the Merseyside region. The bridge spans 1.2 kilometers across the River Mersey, providing a new crossing between Runcorn and Widnes. The construction of the bridge involves advanced engineering techniques, extensive earthworks, and the installation of modern traffic management systems. The bridge is a cable-stayed structure, featuring 3 pylons and a series of cables supporting the bridge deck. Constructing the pylons involves driving deep foundations into the riverbed, using reinforced concrete to ensure stability and durability. The cables are made from high-strength steel, capable of supporting the weight of the bridge deck and the traffic it carries. One of the significant challenges of the Mersey Gateway Bridge project is managing construction in a tidal river environment. Engineers must carefully plan and execute construction activities to minimize disruptions to river traffic and ensure the safety of workers and the environment. Additionally, the project must adhere to strict environmental and safety regulations, requiring advanced monitoring and control systems to mitigate impacts. The bridge incorporates numerous sustainability features, such as energy-efficient lighting, stormwater management systems, and green spaces. These elements reduce the environmental impact of the bridge and enhance the quality of life for nearby residents. The construction also involves extensive public consultation and engagement to address concerns and ensure transparency.
Brightline West will be the first true high-speed passenger rail system in America. making a milestone in the country's transportation landscape. This modern, eco-friendly system will not only redefine train travel by connecting two iconic destinations, Las Vegas and Southern California, but it'll also bring the US up to speed with international high-speed rail standards, popular in regions like Europe and Asia. The project aims to provide a faster, greener, and more efficient alternative to driving or flying, with trains reaching impressive speeds of up to 200 miles per hour. This 218-mile passenger rail service will stretch from Las Vegas to Rancho Cucamonga, California, with 96% of its alignment within the median of the I-15 highway. This strategic placement minimizes land use impact and maximizes direct travel, allowing passengers to enjoy a seamless journey with scenic views along the route. Today, nearly 50 million annual trips occur between Los Angeles and Las Vegas, over 85% of them by car, making the drive a long, unpredictable trip, often plagued by heavy congestion, road delays, and high fuel costs. By replacing these car trips with fast, reliable train service, Brightline West expects to serve more than 9 million one-way passengers annually. This shift is projected to reduce traffic congestion significantly and lower greenhouse gas emissions, offering a sustainable alternative for the busy 270-mile journey and helping the region meet its climate action goals. The first phase of Brightline's West service is expected to begin by 2028, drastically reducing travel time between Las Vegas and Rancho Cucamonga in just about 2 hours and 10 minutes. This efficiency will allow travelers to bypass both the unpredictable road conditions and the time-consuming process of air travel, which includes check-in and security waits. The rail journey will be smooth, relaxing, and importantly, eco-friendly. This high-speed rail project is part of a broader push in the US to modernize its aging transportation infrastructure, with an emphasis on sustainable options. As a fully electric rail system, Brightline West will be powered by renewable energy sources, aligning with California's ambitious clean energy and emissions reduction goals. Furthermore, the Rancho Cucamonga station will integrate seamlessly with local transit, including Metrolink, allowing passengers quick access to the greater Los Angeles area, creating a more connected, transit-oriented future. Once completed, the Brightline West is expected to set a new standard for high-speed rail travel in the US, demonstrating the potential of sustainable, high-speed transit to transform the regional connectivity, reduce travel times, and offer a viable alternative to cars and planes for millions of travelers each year. This pioneering project could serve as a model for other high-speed rail developments across the country, igniting a movement toward cleaner, faster, and more efficient transportation for generations to come.
Imagine discovering a hidden ocean beneath the sands of the Sahara Desert. Water so ancient and vast that it could sustain entire cities and transform one of the driest regions on Earth. That's exactly what Libya found in the 1950s, not through a quest for water, but during an oil exploration mission. Instead of crude oil, they stumbled upon massive underground reservoirs of fossil water, a treasure buried for thousands of years when the Sahara was a lush, green landscape. This discovery gave birth to one of the most ambitious engineering projects in history, the Great Man-Made River. The river is a colossal network of pipes and reservoirs designed to extract this fossil water and transport it across Libya, a country with almost no natural rivers and very little rainfall. Spanning an incredible 4,000 kilometers, longer than many countries, this system delivers up to 6.5 million cubic meters of water every single day. To give you an idea of scale, that's enough water to fill over 2,600 Olympic-sized swimming pools daily. It's not just an artificial river, it's an engineering marvel. At the heart of the river project are massive pipes, each 4 meters in diameter, large enough for a car to drive through. These pipes snake across the desert, carrying water from underground wells to cities along Libya's Mediterranean coast, where most of the population lives. Along the way, the system includes giant reservoirs, human-made lakes that store water for distribution. These reservoirs are lined with materials to prevent seepage and evaporation, preserving every precious drop in a region where water is more valuable than gold. The project's purpose is both straightforward and monumental: to provide water for Libya's coastal cities and support agriculture in some of the driest and harshest conditions on the planet. Before the artificial river, farming in Libya relied heavily on scarce and expensive desalinated water. Today, this artificial river has turned barren desert areas into fertile farmland, enabling the growth of crops and even providing drinking water for millions of people. It's hard to overstate the impact of such a project on a country where water scarcity has always been a critical issue. But like any grand vision, the river comes with its challenges. The most pressing concern is the finite nature of fossil water. Unlike rivers or lakes that are replenished by rainfall, fossil water is a non-renewable resource. Once it's used up, it's gone for good. Scientists estimate that Libya's underground reserves could last a few centuries, but there's no way to refill them once depleted. It's a ticking clock that forces the country to think carefully about how it manages this precious resource. Adding to the complexity is Libya's political instability. Over the years, civil unrest and conflict have threatened the maintenance and security of the river infrastructure. Damaged pipes or reservoirs can disrupt the entire system, cutting off water supplies to millions. For a project of this scale, constant upkeep is non-negotiable, but achieving that in a war-torn region is no small feat. Next up, we have to talk about the Seattle waterfront redevelopment, a transformative project reshaping the shoreline of the city into a world-class urban destination. For decades, Seattle waterfront was dominated by the Alaskan Way Viaduct, a double-decked elevated highway that separated the city from its shoreline. Constructed in the 1950s, the viaduct served its purpose but became outdated, seismically vulnerable, and an eyesore that cut off the city from its vibrant waterfront. In 2001, a 6.8 magnitude earthquake highlighted the instability of the viaduct, sparking discussions about its removal. The solution is a massive redevelopment project that would transform the area into a pedestrian-friendly, environmentally sustainable space. The Seattle waterfront redevelopment spans 20 acres and includes a mix of parks, pedestrian pathways, bike lanes, and upgraded transportation infrastructure. A newly designed Alaskan Way Boulevard will replace the old viaduct, incorporating transit lanes, bike paths, and green spaces to enhance urban mobility. One of the most striking features is the Overlook Walk. It's an elevated pedestrian pathway offering breathtaking views of Elliott Bay while connecting key attractions like the Pike Place Market and the Seattle Aquarium. This walkway is designed to seamlessly integrate with the city, providing both aesthetic appeal and practical connectivity. The redevelopment also includes significant environmental restoration efforts. The project aims to restore the natural habitat, improve stormwater management, and create a healthier marine ecosystem. Shoreline restoration efforts will make the waterfront more resilient to climate change while supporting biodiversity. The Seattle Aquarium expansion is another key component. A new ocean pavilion will be added, showcasing marine life and providing educational experiences. The pavilion will feature immersive exhibits highlighting the importance of ocean conservation, further strengthening the identity of Seattle as a city connected to the water. The total cost of the Seattle waterfront redevelopment is estimated at $756 million. The budget covers everything from transportation upgrades and public spaces to environmental restoration and cultural enhancements. Construction has been a massive undertaking, requiring advanced engineering solutions to support the new infrastructure while minimizing disruptions to daily life. Specialized cranes, earth-moving equipment, and hydraulic pile drivers are being used to build new piers and support structures along the waterfront. Engineers are also employing seismic retrofitting techniques to ensure that new buildings and walkways can withstand potential earthquakes. Currently, the project is in its final stages, with major sections nearing completion. The Overlook Walk is set to open later this year, along with new bike lanes and pedestrian pathways. The Seattle Aquarium expansion is also on track, expected to open its doors to visitors in early 2026. On a site that once lay fallow and largely undeveloped, the construction of Blue Oval Battery Park marked a decisive leap into the future of high-volume electric vehicle component manufacturing. This sprawling industrial complex, designed to support the fabrication and assembly of lithium-ion battery cells and modules, demanded advanced planning and precision across every phase of construction, from grading and utilities to cleanroom commissioning. With a footprint spanning several million square feet, the facility was conceived not merely as a plant, but as a vertically integrated system with embedded energy, safety, and logistics infrastructure tailored for battery production at scale. The project began with large-scale site preparation involving the removal of unsuitable soils, installation of wick drains to accelerate consolidation, and the laying of geotextile fabric beneath engineered fill to stabilize the subgrade. Heavy compaction equipment, GPS-guided grading systems, and automated moisture control were employed to achieve stringent flatness and density tolerances across hundreds of acres. Underground utility corridors were trench cut in parallel with high-capacity storm drains, electrical conduit duct banks, and chilled water supply lines installed in tandem to minimize rework and speed up scheduling. Once the building pad was stabilized, the structural steel phase commenced. Massive steel columns, girders, and joists were prefabricated and brought to site for rapid erection using crawler cranes and aerial work platforms. The roof system, designed to support HVAC units, solar panels, and sprinkler infrastructure, relied on long-span bar joists and insulated metal decking that was continuously welded and mechanically fastened in overlapping sections. Poured-in-place concrete slabs were installed in phased pours using laser screeds and power trowels, with specific areas designed for extra load-bearing capacity to support heavy machinery, battery cell stacks, and chemical storage zones. Critical to the operation of a battery manufacturing facility is the implementation of clean room environments and dry room chambers. These required building envelopes with extremely low air permeability achieved through multi-layer vapor barriers, continuous insulation, and air-sealed panel joints. Mechanical systems included desiccant dehumidifiers, HEPA filtered positive pressure ventilation, and redundant HVAC loops to maintain both particulate and moisture control. Specialized coatings were applied to floor slabs in clean areas, often involving epoxy resin with anti-static properties to protect sensitive electronics and prevent electrostatic discharge during cell handling. Power distribution infrastructure had to be scaled for high-load operations, with on-site substations, high-voltage switchgear, and transformer yards designed to support continuous production. Bus duct systems and flexible conduit networks were installed overhead to provide modular electrical service to production lines, allowing for equipment reconfiguration with minimal downtime. Simultaneously, process piping systems for chilled water, nitrogen, compressed air, and vacuum services were routed through prefabricated utility racks mounted to steel columns. Environmental compliance was a significant design driver. The facility integrated stormwater detention basins, zero-discharge process water recycling, and volatile organic compound filtration systems to meet both federal and state environmental standards. Fire suppression systems had to account for the unique hazards of lithium-based materials, requiring dry chemical suppression in certain rooms and foam-based systems in others, backed by an advanced detection network including thermal imaging and gas sensors. Rising from the urban fabric of downtown Miami, the Miami World Center represents one of the largest and most complex mixed-use developments in the United States, combining residential towers, retail space, hospitality venues, and transportation infrastructure within a tightly confined and highly active metropolitan zone. From an engineering and construction perspective, this multi-block development introduced significant challenges in staging, subsurface coordination, and structural integration across disparate building types, all while maintaining operational continuity in one of Florida's busiest urban centers. Site preparation began with extensive demolition and clearing operations. Much of the project footprint was previously occupied by low-rise commercial buildings and underutilized parcels, which required systematic dismantling and remediation. Excavation crews were tasked with removing foundations, underground storage tanks, and legacy utilities while coordinating with the city to preserve or relocate critical service lines. Due to the high water table, typical of coastal Miami, dewatering systems were installed early in the process, using deep well points and submersible pumps to manage groundwater during foundation work. The structural design of the various towers and podiums involved a combination of reinforced concrete frames and post-tensioned slabs, tailored to meet both vertical load demands and lateral wind forces characteristic of hurricane-prone South Florida. High-rise residential components, some exceeding 50 stories, were supported by deep pile foundations driven into stable limestone strata. These piles were tested using static and dynamic load tests to confirm bearing capacity and settlement behavior prior to full-scale construction. To accommodate multiple uses within tight spatial constraints, engineers designed large podium structures that span entire blocks and house parking decks, retail space, mechanical rooms, and loading docks. These podiums utilized cast-in-place concrete cores and transfer slabs, with integrated fireproofing and acoustic treatments to separate commercial activities from the residential levels above. The coordination of vertical transportation systems, including high-capacity elevators, escalators, and stairwells, was managed using 3D building information modeling to avoid clashes and optimize flow. One of the most technically demanding aspects of the Miami World Center was its subterranean utility coordination. Given the density of existing municipal lines and the proximity to the Metro Rail and Brightline stations, all underground installations, ranging from electrical conduits to stormwater management systems, had to be precisely routed and sequenced. Redundant systems were designed for critical infrastructure, including dual water feeds and backup generators located above flood elevation in compliance with updated coastal resiliency codes. Facade systems for the towers included unitized curtain wall assemblies with insulated glazing and hurricane-resistant frames, assembled off-site and installed using tower cranes and specialized rigging teams. Balconies, a hallmark of Miami residential design, were cantilevered with post-tensioned slab extensions, requiring careful engineering to mitigate deflection and ensure long-term durability in the saline air environment. Finally, staging and logistics played a pivotal role throughout the multi-year construction schedule. With multiple general contractors operating simultaneously on adjacent parcels, vertical and horizontal movement of materials had to be tightly choreographed. Dedicated staging zones, off-site prefabrication yards, and synchronized crane operations minimized congestion and ensured safety across the development. We have to talk about the Samsung chip factory in Taylor, Texas. This $17 billion mega project, propelled by the CHIPS and Science Act, is one of the most ambitious undertakings in US semiconductor history. The commitment of Samsung to the US semiconductor industry dates back to 1978, with substantial investments over the years. This Taylor facility represents the largest single investment of the company in the US, bringing its total US investments to over $47 billion. The plant is part of a broader strategy to enhance domestic chip production, ensuring supply chain resilience and reducing reliance on overseas manufacturing hubs like Taiwan. The project also underscores the strategic collaboration between Samsung and the US government. With $6.4 billion in direct funding from the CHIPS and Science Act, this plant symbolizes a renewed focus on technology-driven economic growth. The Samsung chip factory will produce advanced logic chips for applications such as AI, 5G, high-performance computing, and autonomous vehicles. Covering over 1,200 acres, equivalent to 11 football fields, it is set to become one of the largest buildings in the United States. The facility will house lithography machines, clean room technologies, and advanced packaging capabilities, allowing Samsung to handle every step of chip production domestically. The groundbreaking of the plant occurred in 2022. The design of the facility focuses on sustainability, employing energy-efficient systems and advanced water recycling technologies. This commitment ensures that environmental impacts are minimized, while production efficiency is maximized. This mega project will create 2,000 high-tech jobs and an additional 6,500 construction jobs during its development phase. Beyond these opportunities, the investment by Samsung is expected to spur regional growth, generating 20,000 indirect jobs in Taylor and the surrounding areas. The local economy has already felt the impact, with Samsung injecting $26.8 billion in 2023 alone. The construction of the facility involves cutting-edge methodologies, high-capacity cranes, precision trenches, and advanced robotic systems ensure the structural integrity and operational excellence of the plant. Samsung has incorporated modular construction techniques, enabling rapid assembly while maintaining quality standards. The foundation of the plant and utilities are designed to support additional expansions, including a second fabrication plant already in progress. Samsung Chip Factory will help the United States achieve its goal of producing 20% of the world's logic chips by 2030.
The Brasilia Digital TV Tower is a landmark structure in Brazil, designed by renowned architect Oscar Niemeyer. The tower stands at 600 feet tall and serves both as broadcast facilities and a tourist attraction. The construction of the tower involves advanced engineering techniques and careful architectural design to ensure its functionality and aesthetic appeal. The tower's foundation is a critical component, requiring deep piles driven into the ground to support the massive structure. These piles are typically made of reinforced concrete, providing the necessary strength and stability. The main structure is composed of a reinforced concrete core, surrounded by steel framework. This combination of materials ensures the tower is both strong and flexible, capable of withstanding wind loads and other environmental forces. One of the unique features of the Brasilia Digital TV Tower is its observation deck, located near the top of the structure. Constructing the deck involves installing large glass panels and steel supports to create a safe and accessible space for visitors. The deck provides panoramic views of the city, making it a popular tourist destination. The tower also houses advanced broadcasting equipment, including antennas and transmitters for digital TV signals. Installing this equipment requires precise engineering and coordination to ensure optimal signal strength and coverage. The equipment is housed in specially designed rooms within the tower, protected from environmental factors and easily accessible for maintenance. In addition to its technical functions, the Brasilia Digital TV Tower is an architectural masterpiece, embodying Niemeyer's vision of fluid organic forms. The construction process required collaboration between engineers and architects to ensure the structure's aesthetic integrity while meeting functional requirements. The tower's sleek modern design is a testament to Brazil's commitment to innovation and progress.
Bay Area Rapid Transit Expansion is the next project on our list. If you live in or around San Francisco, you probably know how essential BART is for getting around. The Bay Area is one of the most densely populated regions in California, projected to include over 9 million people by 2040. That's why BART is undergoing its biggest expansion. The Silicon Valley Extension is a $6 billion project designed to extend BART service deeper into Silicon Valley, eventually reaching San Jose. This isn't just about adding more tracks. Phase 2 of the expansion will see the construction of 3 brand new underground stations. There will be a massive tunnel boring machine cutting through downtown San Jose. By 2026, commuters will have a faster, cleaner, and more efficient way to travel. Now let's dive into some impressive engineering behind this massive project. BART is relying on cutting-edge tunnel boring technology for the underground portion of the extension. Tunnel boring machines are essentially underground factories. These colossal machines can measure over 300 feet long and weigh up to 3,000 tons. As they dig, TBMs simultaneously install precast concrete segments to reinforce the tunnel walls, speeding up the construction process by ensuring the tunnels are structurally sound. In the future, they'll easily withstand the natural movements of the Earth. What's even more impressive is the scale of the Silicon Valley extension. At 6 miles, it's the largest public infrastructure project ever attempted in Santa Clara County. Think of the impact of 4 new stations on the daily lives of thousands of commuters. 28th Street, Little Portugal, downtown San Jose, Durandon, and Santa Clara. Each station is designed to handle the growing number of people commuting in the Bay Area. With an estimated completion date of 2026, this extension promises to revolutionize the way people travel, saving precious hours each day. The Train Control Modernization Project is one of the major elements tied to this expansion, enabling trains to run more frequently and reliably, allowing you to catch the next one without a long wait. This technology will enable trains to run closer together, especially during peak hours. It's not just about adding more tracks, it's about optimizing the existing system to maximize capacity. By 2040, BART aims to transport nearly 55,000 passengers daily on this extended system. That's a staggering number, reflecting the growing demand for efficient public transportation in the Bay Area. But with great ambition comes great cost. The total cost of Phase 2 has escalated from $4.7 billion to a staggering $12.8 billion. Despite this massive price tag, the potential benefits are beyond expectations. Reduced traffic congestion, faster commutes, and a more sustainable transit system make this investment a worthwhile effort. BART's fleet of the future is not just about adding more trains, it's about revolutionizing the passenger experience. These new energy-efficient trains are designed to be quieter, more accessible, and more comfortable. Commuters will experience smoother, quieter rides with better amenities. This modernization effort, coupled with the Silicon Valley extension, is part of a larger vision, Link 21. BART aims to build a new Transbay rail crossing, alleviating congestion on the existing Transbay tube and increasing capacity for both BART and regional rail services.
A brand new waterway cutting through one of the most iconic cities in the world, connecting the Black Sea to the Mediterranean and revolutionizing global shipping. That's exactly what Turkey's Istanbul Canal aims to achieve. This 50-kilometer canal, stretching across the European side of Istanbul, is one of the most ambitious infrastructure projects in recent history. And while it's still under construction, its potential to reshape global trade is undeniable. Which brings us to the big question: why build a new canal when you already have the Bosphorus Strait? The answer lies in the strait's limitations. The Bosphorus is one of the busiest and narrowest natural waterways in the world. Every year, tens of thousands of ships pass through it, including massive oil tankers carrying millions of tons of crude oil and chemicals. This heavy traffic creates serious risks, from accidents to environmental disasters like oil spills, which could devastate the marine ecosystem and harm the surrounding communities. The Istanbul Canal offers a solution, providing an alternative route to reduce congestion in the Bosphorus and safeguard the environment. The canal is designed to be 25 meters deep and 350 meters wide, making it capable of accommodating the largest ships and submarines. To put it in perspective, these dimensions are significantly larger than many existing canals, allowing vessels that might struggle in other waterways to pass through with ease. Imagine towering container ships gliding effortlessly through the canal, carrying goods from Asia to Europe and beyond. The sheer size and capacity of the Istanbul Canal could make it a new heavyweight in global shipping. But this canal isn't just about relieving traffic or boosting trade. It's also about positioning Istanbul as a central hub for international shipping. Sitting at the crossroads of Europe and Asia, Istanbul has always been a vital link in global trade. With the canal, Turkey is doubling down on this advantage, aiming to rival the likes of the Suez and Panama canals in importance. It's a bold vision, but one that could turn Istanbul into a logistical powerhouse, drawing in business from around the world. What's fascinating about the Istanbul Canal is how it ties into Turkey's broader economic goals. This isn't just a standalone project, it's part of a larger plan to develop the surrounding area into a thriving hub of activity. New ports, logistics centres, residential developments, and even recreational facilities are being built alongside the canal. The hope is that this will not only boost trade, but also create jobs and spur economic growth for the entire region. Of course, no project of this magnitude comes without its challenges. The canal has faced criticism, both at home and abroad. Environmentalists worry about the potential impact on local ecosystems, particularly with the large-scale excavation and changes to water flow. Then there's the cost, estimated at around $15 billion, which has sparked debates about whether the investment is worth it. Despite these concerns, the Turkish government remains committed to the project, viewing it as a long-term asset that will pay off for generations to come. If the Istanbul Canal lives up to its promise, it could fundamentally change the way goods move across the globe. Could they become the next big name in global shipping? Let's talk about the Sunzia Wind and Transmission Project, one of the most ambitious renewable energy projects in the United States. Located in New Mexico and Arizona, this massive undertaking is set to become the largest wind energy infrastructure in the Western Hemisphere. With a staggering 3,500 megawatts of wind power capacity, Sunzia aims to transform the energy landscape by delivering clean electricity to millions of homes across the Southwest. The history of the project dates back to 2006, when initial discussions began about building a large-scale transmission system to utilize the vast wind energy potential of New Mexico. After years of environmental reviews, regulatory approvals, and legal challenges, the project was finally greenlit, with full construction commencing in 2023. The significance of Sunzia cannot be overstated. The project will play a crucial role in reducing the regional dependence on fossil fuels, cutting down carbon emissions by millions of metric tons annually. It will also enhance grid reliability, allowing states like California and Arizona to meet their ambitious renewable energy targets. The construction plan involves two key components: the Sunzia wind farm, spanning thousands of acres in New Mexico, and the Sunzia transmission line, a 550-mile-long, high-voltage, direct current system stretching from central New Mexico to Arizona. The transmission line is designed to carry clean energy across state borders, ensuring efficient distribution to major urban centers. The features of this mega project make it a technological and engineering marvel. The wind farm will host hundreds of massive wind turbines, each standing over 650 feet tall, utilizing advanced turbine technology to maximize energy output. Meanwhile, the transmission system will incorporate cutting-edge HVDC infrastructure, reducing energy loss over long distances and improving the overall efficiency of the grid. The budget for Sunzia is estimated at $8 billion, making it one of the most expensive renewable energy projects in the country. The construction process is a massive logistical operation, requiring specialized heavy lift cranes to install wind turbines, drilling rigs for foundation work, and high voltage transmission line equipment to lay the massive electrical infrastructure. Additionally, large-scale concrete pouring operations ensure the stability of turbine foundations, while fleet vehicles transport materials across the remote construction zones. Currently, the Sunzia wind farm is progressing rapidly, with turbine installations nearing completion. The transmission line construction is also well underway, with major sections already erected and testing phases beginning. Full project completion is expected by 2026, making it a game changer in the renewable energy sector. Once operational, Sunzia will supply clean electricity to over 3 million homes, marking a historic milestone for sustainable energy in the United States. Stretching across the southern portion of Florida, the Everglades represents one of the most unique and delicate ecosystems in North America, and the series of restoration projects aimed at rehabilitating this landscape stand as some of the most ambitious hydrological engineering efforts ever undertaken in the United States. These projects collectively focus on undoing decades of human alteration that disrupted natural water flows, severely impacted wildlife habitats, and degraded water quality. The engineering challenges associated with these efforts are vast, involving large-scale earth-moving, hydrological modeling, structural water control features, and long-term adaptive management. At the heart of the restoration initiative is the re-establishment of natural sheet flow, which refers to the slow, shallow movement of water southward across the Everglades flat terrain. Historically, this flow was interrupted by the construction of levees, canals, and pumping stations that redirected water for urban and agricultural uses. To address this, engineers have designed and constructed massive flow equalization basins, stormwater treatment areas, and pump stations that carefully mimic the timing and volume of historical water deliveries. One of the key undertakings involved the removal or modification of hundreds of miles of canals and levees, such as the partial deconstruction of the Miami Canal and the rerouting of flow into restored wetland corridors. This work required precise excavation and reshaping of land to ensure that water could once again disperse evenly and slowly across the landscape. Earth-moving operations were executed with amphibious excavators and low ground pressure tracked vehicles to reduce soil compaction and environmental disruption. In areas where water storage was a major constraint, large reservoirs were constructed, some exceeding tens of thousands of acre-feet in capacity. These reservoirs are lined and equipped with high-volume inflow and outflow structures controlled by gated spillways and electrically operated valves. Their purpose is to capture stormwater during wet seasons and release it in a controlled manner during dry periods, mimicking natural hydrological cycles. Adjacent to these reservoirs are extensive stormwater treatment areas composed of shallow, vegetated cells that use aquatic plants like cattails and submerged vegetation to remove excess phosphorus and other nutrients. The restoration projects also necessitated the construction of extensive culvert networks and bridges to allow water to pass underneath roadways, particularly along major east-west transportation corridors such as Tamiami Trail. These structures were designed to accommodate large volumes of slow-moving water without impeding traffic or causing structural undermining. The foundations of these bridges were pile-driven deep into stable substrata, and the superstructures were built using pre-stressed concrete beams capable of withstanding Florida's corrosive and humid environment. Monitoring infrastructure is integrated throughout the system, including flow gauges, water quality sensors, and automated telemetry stations. Data collected from these devices feed into centralized control systems that allow engineers and hydrologists to make real-time adjustments to water releases, ensuring ecological targets are met. The adaptive management strategy also includes provisions for ongoing modifications as performance data accumulates over years of operation. Mega projects symbolize human ambition at its finest, but some of them go so far beyond the ordinary, they redefine what's possible. They're billion-dollar ventures that span continents and reshape entire cities, from the tallest dams conquering nature to bridges stretching on for miles. Today, we're diving deep into gigantic mega projects you've never seen. Let's travel over to the Khavda Solar Park mega project in India, a colossal renewable energy initiative that aims to redefine how we power our future. Located in the Kutch district of Gujarat, this $18 billion solar park is set to be one of the largest solar projects in the world. Upon completion, Khavda Solar Park will span 72,600 hectares of wasteland, integrating solar panels and wind turbines to generate clean energy. The composition of the park includes hybrid wind-solar zones and dedicated wind power zones. Solar power generation peaks during the day, while wind power can supplement during evenings and nights, optimizing energy output. Developers like Adani Green Energy, National Thermal Power Corporation, and Gujarat State Electricity Corporation are key contributors, with the hybrid zones in the park capable of producing 9.5 gigawatts alone. The Power Grid Corporation of India manages the vast transmission infrastructure of the park, ensuring seamless energy distribution. Khavda Solar Park is a key step in the ambitious plan of India to achieve 500 gigawatts of renewable energy capacity by 2030. The project is expected to generate over 15 gigawatts of solar power, providing clean energy to millions of homes and businesses. The construction of Khavda Solar Park involves state-of-the-art photovoltaic modules and energy storage systems designed to ensure efficiency. With advanced robotic cleaning systems and AI-driven monitoring, this project aims to maximize energy production while minimizing operational costs. Machinery like trenchers, pile drivers, and heavy-duty cranes have been employed to speed up the construction process. Developers have deployed advanced photovoltaic modules to enhance efficiency. The hybrid wind-solar zone includes projects which commissioned its first 1 gigawatt capacity in March 2024 with 2.4 million photovoltaic modules. By July 2024, the first 250 megawatts of the park wind power capacity came online. An additional 23,000 hectares are reserved for wind power, with the Solar Energy Corporation of India conducting competitive bidding to allocate this space. To complement this, the government plans to install a 14 gigawatt-hour grid-scale battery storage system, further enhancing the reliability and capacity of the park. The park is expected to power 18 million homes, creating over 100,000 jobs and attracting approximately $17 billion in investments. It is also projected to reduce carbon emissions by 5 crore tons annually, making a significant contribution to the Indian climate goals. The foundation stone was laid by Indian Prime Minister Narendra Modi in December 2020. The park is expected to reach its full completion by December 2026.
The Central Wan Chai Bypass in Hong Kong is a major infrastructure project designed to improve traffic flow and reduce congestion in the city. The project involves constructing a 4.5-kilometer long highway, including a 3.7-kilometer tunnel connecting Central and Wan Chai. The construction of the bypass involves advanced tunneling techniques, extensive earthworks, and the installation of modern traffic management systems. Tunneling for the bypass employs tunnel boring machines to excavate and install tunnel segments simultaneously. This method ensures the tunnels are structurally sound and minimize disruptions to the surface. The tunnels are lined with precast concrete segments, providing durable and waterproof structure. The construction of the highway involves extensive earthworks, including excavation, grading, and paving. The highway is designed to accommodate high traffic volumes, requiring precise engineering to ensure smooth and safe traffic flow. Additionally, the project includes the installation of modern traffic management systems such as variable message signs and traffic cameras to monitor and control traffic in real time. One of the significant challenges of the Central Wan Chai Bypass project is managing construction in a densely populated urban environment. Engineers must carefully plan and execute construction activities to minimize disruptions to daily life and ensure the safety of workers and residents. Additionally, the project must adhere to strict environmental and safety regulations, requiring advanced monitoring and control systems to mitigate impacts. Moreover, the bypass incorporates numerous sustainability features, such as noise barriers, green walls, and energy-efficient lighting. These elements reduce the environmental impact of the highway and enhance the quality of life for nearby residents. The construction also involves extensive public consultation and engagement to address concerns and ensure transparency.
Next, the East San Fernando Valley Light Rail Transit Project is about connecting communities. This $3.6 billion project aims to transform public transport in the San Fernando Valley, an area notorious for its gridlock traffic. This rail transit project is being developed by the Los Angeles County Metropolitan Transportation Authority. The goal is simple: to transform how residents move through the valley. Phase 1 of the project, covering 6.7 miles and 11 stations, is expected to be operational by 2028. The new line will primarily run along the Van Nuys Boulevard and will connect key areas like Van Nuys, Panorama City, Arleta, and Pacoma. For a region where traffic can be soul-crushing, the light rail system will serve as a lifeline, helping commuters save time and money while reducing carbon emissions. What sets this project apart is the engineering technologies and planning behind it. Imagine a sleek, efficient light rail system powered by overhead electricity. The OCS system, fueled by 14 traction power substations, will ensure reliable and environmentally friendly operation. The light rail vehicles will offer ample space for up to 400 passengers. Let's discuss the sustainable design of the project here. Each station along the route will be equipped with shading devices to protect passengers from the Southern California sun. Canopies will be designed with sustainable features, such as the ability to accommodate solar panels, making the entire system eco-friendly. With a maximum operational speed of 104.6 kilometers per hour, you'll reach your destination quickly and efficiently. This project is more than just technology and speed. The community played a vital role in shaping its design. Back in 2013, residents of the area were presented with multiple transit options. Finally, they chose light rail as their preferred transit option. This means that the new system isn't just a top-down decision, it's a response to the community's needs and desires. The station designs will incorporate art that reflects the diverse cultures and histories of the surrounding communities, making each stop unique and a point of pride for residents. The future of transportation in the San Fernando Valley is taking shape. Utility relocation for the East San Fernando Valley Light Rail Transit Project began in late 2022, marking a significant milestone. This project will be completed in 2 phases, with the first phase expected to be finished by 2028. The second phase will bring 9.2 miles of track and 14 stations to the region. This will connect the Metro G line to Metrolink, making regional travel more convenient than ever. Imagine cruising through one of the busiest areas in Los Angeles without ever hitting the brakes.
We have to talk about One River North, a stunning biophilic skyscraper in Denver, Colorado. With its breathtaking biophilic design, the tower redefines how nature and urban development can coexist. The structure features a dramatic canyon-like opening carved into its facade, filled with lush greenery, cascading waterfalls, and elevated walkways. Denver is known for its proximity to the Rockies, and One River North is a tribute to the natural beauty of the region. Designed by Mad Architects, a globally recognized firm known for its futuristic and nature-inspired designs, this 42-story residential tower seeks to revolutionize urban living. Rather than isolating residents in glass and steel, the design integrates outdoor elements within the vertical structure. This megaproject is a high-rise residential tower, with features hardly seen unlike any other in the world. The most striking feature of the building is its gash, a deep cut that runs across multiple floors, resembling a mountain ravine filled with vegetation and flowing water. This design serves both an aesthetic and functional purpose. It introduces natural ventilation, daylighting, and an open-air experience in the middle of a skyscraper. The tower includes 187 luxury residences, each designed to maximize natural light and panoramic views. Residents will have direct access to over 13,000 square feet of green space, featuring elevated walking paths, relaxation areas, and water elements. The rooftop garden offers unobstructed views of the Rocky Mountains, while a private club and spa ensure that residents have access to luxury wellness amenities. One River North is being developed with an estimated budget of $250 million. While the cost is significant, the engineering challenges involved in creating a vertical canyon within a skyscraper justify the investment. Traditional skyscrapers rely on rigid core structures to ensure stability, but the open-air canyon design of this mega project presented unique structural challenges. To maintain the integrity of the building, engineers had to develop wind-resistant support structures that could withstand varying weather conditions in Denver. The deep cut of the canyon required innovative load distribution techniques, ensuring that the building remained structurally sound despite its massive opening. Advanced reinforced concrete and steel frameworks were used to stabilize the structure, while a high-tech irrigation system ensures that the greenery remains lush throughout the year. Currently, One River North is in its final stages of construction, with interior finishes and landscaping being completed. The building is expected to open in mid-2025, and apartments are already selling at record-breaking prices due to the high demand for nature-integrated urban living spaces. Afghanistan isn't the first country you think of when it comes to ambitious engineering projects. Yet, amidst all this turmoil, the country is working on something extraordinary: the Kosh Tapa Canal. At 152 meters wide and 8.5 meters deep, the 285-kilometer long Kosh Tapa Canal is a marvel of modern engineering, especially considering where it's being built. The project starts at the Amu Darya River in the Balkh province and snakes its way through Jowzjan and Faryab provinces. The project's purpose is to bring desperately needed water to one of the driest regions in the world, where droughts and food shortages have made life incredibly hard for farmers and rural communities. Afghanistan has long struggled with water scarcity, a problem worsened by climate change, declining groundwater levels, and years of underdeveloped infrastructure. The Kosh Tapa Canal is a bold solution to this crisis. Once completed, it will provide water to over 1 million people and transform 55,000 hectares of desert into fertile farmland. But this isn't just about growing food. The canal represents a vision for Afghanistan's future. The goal is to not only achieve food security, but to turn the country into a wheat exporter by 2028. It's a plan that could drastically change the lives of countless Afghan families, offering them stability and independence in a way that hasn't been possible for years. Building such a colossal canal in a country like Afghanistan comes with a unique set of challenges. Resources are scarce, international aid is limited due to sanctions, and the constant threat of conflict looms over the project. Yet, the Afghans are pushing ahead with determination. Using aging equipment and relying solely on local expertise, they've already completed about half of the canal. One of the most interesting aspects of the Kosh Tapa Canal is its design. Unlike many modern waterways, the canal is unlined. No concrete walls or floors here. At first glance, this might seem like a cost-cutting measure, and it is, but there's more to it. By leaving the canal unlined, water can seep into the ground, naturally recharging underground reservoirs. This approach helps ensure there's water available even during dry spells, making the canal a long-term solution rather than just a quick fix. The benefits of the canal are already starting to show. Villages along its banks are gaining access to clean water for the first time in years, and new farms are popping up as the project progresses. Farmers who had abandoned agriculture due to drought are returning to their fields, planting crops that will feed their families and fuel the local economy. The project is also creating jobs, thousands of them, bringing much-needed income to communities that have been neglected for decades. Few civil engineering efforts in North America rival the logistical scale and environmental complexity of the Sioux Locks Expansion project in Sault Ste. Marie, Michigan. At the heart of this endeavor lies the construction of a new, modern lock chamber to replace the aging and underutilized Davis and Sabin locks, making way for a structure capable of accommodating the largest Great Lakes freighters, vessels over 1,000 feet long and carrying over 70,000 tons of iron ore per trip. Planning for this mega project required extensive geotechnical investigation, structural design coordination, hydraulic modeling, and phased construction that could integrate with ongoing lock operations and preserve commercial navigation throughout the build. The initial step involved dewatering a large section of the existing canal where the new lock would be constructed. This required the installation of steel sheet pile cofferdams driven deep into bedrock, reinforced with cross-bracing and anchored to resist the immense hydrostatic pressure of the St. Mary's River. Once the cofferdams were sealed and dewatering pumps reduced the water table, excavation of glacial till, cobble, and fractured bedrock began. Controlled blasting was necessary to remove heavily jointed bedrock layers, and each detonation was carefully monitored to avoid damaging adjacent structures or disrupting vessel traffic in the nearby Poe and MacArthur locks. As excavation reached design depth, foundation preparation involved smoothing and cleaning the bedrock surface, followed by the placement of mass concrete footings and pile caps. High-strength concrete with low permeability characteristics was used to ensure durability in this highly saturated freeze-thaw environment. Reinforcing steel cages, prefabricated and lowered into place using tower cranes, formed the basis of massive vertical lock walls. Each section was cast using slip-form techniques, allowing continuous concrete pours to maintain quality and avoid cold joints. Embedded within the lock walls were corrosion-resistant mechanical systems, including gate recesses, pintle bearings, and hydraulic conduits. The lock gates themselves represent a significant engineering milestone. Designed as mitre gates with steel skin plates and internal trusses, they are fabricated offsite and floated into place via barge, then lowered into sockets, machined into the concrete floor. Each gate weighs several hundred tons and must align precisely to ensure a watertight seal. Adjacent to the gates, culvert valve chambers and culvert galleries were constructed to control the massive volumes of water used to fill and empty the lock chamber. These culverts, embedded within the lock's concrete walls and floor, operate using gravity-fed systems regulated by bulkhead slots and hydraulically actuated valves, optimized for smooth water transitions to minimize turbulence. Maintaining construction access in such a confined and operationally sensitive area demanded a high degree of sequencing. Staging areas were created along both riverbanks, with temporary trestles and barge-mounted cranes deployed for material handling. All construction activities had to comply with stringent environmental regulations, including sediment control, aquatic habitat protection, and water quality monitoring. Ice control systems were integrated into the final design, including bubbler lines and heating elements to prevent freezing in critical mechanical assemblies during winter operations. In the southeastern corridor of the United States, where infrastructure development often grapples with both dense urbanization and expansive wetlands, the construction of the Brightline high-speed rail line connecting Miami to Orlando represented a major engineering endeavor. This privately funded rail project was designed not only to introduce high-speed rail to Florida, but also to demonstrate the viability of higher-speed passenger rail service within existing and constrained right-of-way corridors. The execution of this project required a comprehensive integration of new track construction, upgrades to existing freight corridors, and the implementation of advanced signaling and safety systems. Initial site work commenced with a detailed geotechnical analysis of the entire corridor, which spanned over 200 miles. This included evaluating soil stability, drainage characteristics, and subsurface conditions, particularly through the swamp-prone regions of Central Florida. In areas where existing tracks were used, such as the Florida East Coast Railway corridor between Miami and Cocoa, crews had to reinforce subgrades, replace worn ballast, and realign curves to support sustained higher speeds. Track geometry was meticulously adjusted using specialized rail alignment equipment to ensure smooth transitions and compliance with Federal Railroad Administration safety criteria. For the new segment between Cocoa and Orlando, a greenfield corridor was constructed largely along the State Road 528 Expressway median. This presented its own suite of engineering challenges, notably the design and construction of elevated track sections and bridges over sensitive wetlands and stormwater retention zones. Precast concrete girder spans were transported and installed using massive mobile cranes to expedite assembly and minimize environmental impact. Track beds along this route were laid on compacted sub-ballast, topped with engineered ballast layers, ensuring long-term durability under the dynamic loads imposed by high-speed rail operations. The track system employed continuously welded rail, which was delivered in long segments to reduce the number of expansion joints and improve ride quality. Rail thermite welding teams were deployed to join these segments on site with strict quality control to ensure alignment and weld strength. Dual track configurations were introduced in several key sections to allow bi-directional travel and service flexibility, especially near the Orlando International Airport terminus. Stations were another significant component of the build. The Miami Central Station, integrated into downtown Miami, required a complex vertical design solution involving multi-level platforms, elevated passenger concourses, and integrated commercial development. Structural steel framing supported concrete deck slabs, and the entire facility was constructed above active roadways and in proximity to other mass transit systems, necessitating rigorous coordination and sequencing of construction activities. Advanced signaling and communication systems were installed throughout the corridor, including positive train control, to ensure operational safety at high speeds. Grade crossings along the route were upgraded with quad gate systems, median separators, and enhanced warning devices to reduce the risk of vehicle-train interactions. Along the newer segments, full-grade separation was implemented via underpasses or overpasses. Let's discuss Qiddiya, a massive entertainment, sports, and cultural city currently under development near Riyadh, Saudi Arabia. Part of the Saudi Vision 2030 program, Qiddiya was first announced in April 2017. The goal was to diversify the economy, reducing reliance on oil, and boosting domestic spending on entertainment. This $40 billion initiative, funded by the Saudi Public Investment Fund, is a bold step towards positioning the country as a global tourism leader. Covering over 334 square kilometers, Qiddiya is envisioned as the entertainment capital of Saudi Arabia, with attractions designed to cater to a wide audience. By 2030, the project aims to attract 17 million annual visitors, making it the largest tourism destination in the world. Beyond entertainment, Qiddiya is expected to create approximately 325,000 jobs, significantly contributing to the economic diversification in Saudi Arabia. Six Flags. Qiddiya is in the heart of Qiddiya and will be the largest theme park in the Middle East. Spanning 79 acres, the park promises record-breaking attractions, including Falcon's Flight, the world's fastest, tallest, and longest roller coaster, and the world's tallest drop tower. Dragon Ball theme park, developed in collaboration with Toei Animation, is another highlight. It will feature over 30 attractions, including a 70-meter-high Shenron statue housing a roller coaster. Qiddiya Speed Park, an FIA Grade 1 motor racing circuit, will cater to motorsport enthusiasts and is set to host Formula One races by 2027. The park also plans to integrate with the Six Flags attractions, creating a unique blend of motorsports and amusement. Beyond entertainment, Qiddiya will offer cultural attractions such as museums, art galleries, and performing arts venues. The city will also include residential areas, commercial spaces, and a variety of recreational facilities, making it a desirable place to live and work. Construction began in early 2019, with the initial phase originally scheduled for completion in 2023. However, delays have pushed the timeline back, with major projects like the Formula One racetrack and Six Flags still under construction. Advanced construction techniques, including modular building systems and digital twins, are being employed to ensure efficiency and sustainability. Renewable energy sources will power the infrastructure, aligning with Saudi green initiatives.
The Qatar Metro is an ambitious urban rail project designed to transform public transportation in Qatar. This metro system comprises 4 lines: red, green, gold, and blue, spanning a total of 300 kilometers and including over 100 stations. The construction of Qatar Metro involves advanced tunneling techniques, station construction, and the installation of the state-of-the-art train control systems. Tunneling for the metro lines employs tunnel boring machines, which are large cylindrical machines that excavate and install tunnel segments simultaneously. These machines can operate 24/7, significantly speeding up the construction process. The tunnels are lined with precast concrete segments, which are assembled as the TBM advances. This method ensures the tunnels are structurally sound and resistant to groundwater ingress. Station construction involves creating large underground spaces capable of accommodating thousands of passengers daily. Each station is designed with multiple levels, including concourses, platforms, and service areas. The construction process includes extensive excavation, concrete pouring, and steel reinforcement to create durable, safe, and accessible stations. Additionally, the stations are equipped with advanced safety and ventilation systems to ensure passenger safety and comfort. The train control systems for the Qatar Metro are highly sophisticated, employing automated train operation technology. This system allows for driverless train operation, improving efficiency and reducing the risk of human error. The ATO system is integrated with advanced signaling and communication systems, ensuring smooth and safe train movements throughout the network. One of the significant challenges of the Qatar Metro project is managing construction in a densely populated urban environment. Engineers must carefully plan and execute construction activities to minimize disruptions to daily life and ensure the safety of workers and residents. Additionally, the extreme weather conditions in Qatar, particularly in the high temperatures, require special considerations for worker safety and construction materials. Furthermore, the project includes the development of a comprehensive support infrastructure, such as maintenance depots and control centers, to ensure the long-term operation and maintenance of the metro system. These facilities are equipped with advanced diagnostic and maintenance tools to ensure the reliability and safety of the trains and infrastructure.
And let's not forget about the Santa Clara Project, a massive $8 billion urban development project, spanning 240 acres. It's about creating a whole new city within a city. The Santa Clara Project is set to be completed in phases, with the first phase already underway. Phase 1, known as the Tasman East Block, will feature a mix of office spaces, retail shops, and residential units, including affordable housing options. This phase alone will include 39,950 square meters of office space, 4,650 square meters of retail space, and a 480-room hotel. The underground parking garage, with a capacity of 1,900 vehicles, will also be constructed there. Following the completion of Phase 1, future phases will focus on expanding residential areas, adding more green spaces, and constructing additional office complexes. By the time the project is fully completed, it will boast over 156,000 square meters of residential space, with 170 units designated as affordable housing, along with 65,000 square meters of hotel space and 743,000 square meters of retail and restaurant space. These numbers reflect the scale and ambition of the project, which is expected to transform Santa Clara into a major urban hub. One of the most exciting aspects of the Santa Clara project is the 14.2 hectare Central Park. This expansive green space will be the heart of the community, offering residents and visitors a place to relax, exercise, and enjoy the outdoors. In addition to the Central Park, the project will feature over 10 hectares of additional open spaces. Imagine a future where your car drives itself or you commute by air taxi. The Santa Clara project is paving the way for this exciting future. That's not all though. This bustling metropolis will also feature a global food market, offering a culinary journey around the world. With a variety of retail shops, theaters, and concert spaces, Santa Clara is all set to become a cultural hub.
Let's travel over to the Indy 11 Stadium, set to redefine sports culture in Indianapolis, bringing a state-of-the-art soccer facility to the heart of the city. With a budget of $1 billion, This project is a multi-use entertainment hub that will host not only soccer games, but also concerts, community events, and other sporting activities. The development is seen as a key step in elevating the profile of Indy 11, the professional soccer team of the city, while also contributing to the local economy. For years, Indianapolis has been known for its rich sports heritage, hosting the Indianapolis 500, NCAA tournaments, NFL, and NBA games. However, the city lacked a dedicated stadium for its professional soccer team, Indy 11, which had been playing at different venues, including Lucas Oil Stadium and Carroll Stadium. The absence of a permanent home was limiting the ability of the team to build a strong fan base and establish itself as a major force in American soccer. The Indy 11 Stadium is designed as a world-class facility capable of hosting Major League Soccer games in the future. It will have a retractable roof, allowing it to be used in all weather conditions, making it a year-round venue for various events. The stadium will have a seating capacity of 20,000, with room for expansion in case of future demand. One of the standout features of the stadium is its eco-friendly turf, which will provide a high-quality playing surface while minimizing environmental impact. Additionally, the venue will be equipped with energy-efficient LED lighting, reducing electricity consumption. The massive jumbotron of the stadium, one of the largest in the region, will enhance the game day experience for fans with high-definition replays, live stats, and immersive visuals. With a $1 billion budget, the Indy 11 Stadium is one of the largest sports investments in the history of Indiana. The construction process involves massive excavation work, requiring heavy-duty earth-moving machinery, cranes, and drilling rigs to prepare the foundation. High-performance steel and reinforced concrete are being used to construct the framework of the stadium, ensuring structural durability for decades. Engineers are employing advanced prefabrication techniques to assemble certain sections off-site, reducing construction time and improving efficiency. The retractable roof is one of the most complex engineering feats in the project, requiring precision steel fabrication and hydraulic systems for smooth operation. Currently, the construction is well underway, with the main structural framework nearing completion. Interior work, including seating installation and turf placement, is expected to be finished by mid-2025. It began as a symbol of architectural ambition and multimodal integration. The Michigan Central Station in Detroit was originally conceived not just as a terminal, but as an infrastructure centerpiece that fused classical design with early 20th century rail logistics. Constructed beginning in 1910 and completed by 1913, the building rose from reinforced concrete foundations with structural steel framing, clad in limestone and brick masonry. Its Beaux-Arts facade, framed by Corinthian columns and ornamental cornices, concealed an internal structure engineered to support heavy dynamic loads associated with constant passenger traffic, mechanical systems, and vertical elevator shafts that once serviced the upper floors. The station's main concourse featured a vaulted ceiling with Guastavino tile archwork supported by large span steel girders, designed to accommodate both vertical thrust and lateral sway caused by thermal expansion. The train shed, located behind the main terminal, consisted of steel trusses resting on load-distributing concrete piers. These trusses were calculated to handle not only the weight of the shed itself, but also the vibration and impact loading from multiple locomotives and railcars, operating simultaneously across several parallel tracks. Drainage systems beneath the platforms collected stormwater and redirected it to below-grade retention vaults, an early example of urban runoff management. When it entered service, the station's integration with the Michigan Central Railway meant that both freight and passenger traffic could converge seamlessly, requiring the embedding of mechanical interlockings, signal rooms, and baggage routing corridors beneath the main lobby. The building's vertical tower, reaching over 200 feet, housed office floors originally intended for rail administration and later leased to a variety of commercial tenants. These upper floors were framed with cast-in-place concrete slabs supported by riveted steel beams and girders, fireproofed with terracotta tile encasements. As rail use declined in the mid to late 20th century, the structure deteriorated rapidly. Structural integrity assessments conducted in later decades revealed extensive water intrusion, freeze-thaw damage to masonry, and corrosion of steel members, particularly in the floor assemblies and roof truss systems. Restoration efforts required a sequential approach, beginning with structural stabilization. This involved shoring up weakened beams, replacing spalled concrete, and reinforcing the floor diaphragms with steel plates and epoxy-bonded carbon fiber where appropriate. Interior restoration was no less complex. Historical preservation teams catalogued and removed original architectural features, marble panels, plaster reliefs, ornamental ironwork, for off-site restoration. Meanwhile, MEP engineers designed entirely new utility systems to be discreetly integrated behind historic walls and under floor spaces, including chilled water HVAC systems, high-efficiency LED lighting arrays, and digitally controlled fire suppression and alarm infrastructure. These had to comply with modern building codes without disrupting the station's preserved aesthetic. Elevators and stairwells were either restored or replaced, and new vertical access cores were cut through abandoned service shafts, requiring careful structural reinforcement to avoid compromising existing load paths. Additionally, accessibility upgrades included ramps, widened entrances, and elevator service extending to all public floors, all designed to meet ADA standards while blending with the original design. Anchored along the banks of the St. Johns River in downtown Jacksonville, the development of Riverfront Plaza required a deliberate fusion of civil engineering, landscape architecture, and waterfront resiliency planning. The site, once occupied by the old Jacksonville Landing Marketplace, was reimagined as a dynamic public space integrating structural components with flood mitigation strategies, all while maintaining connectivity to adjacent urban infrastructure. From a construction and engineering standpoint, this project represented a complex interplay between environmental restoration, soil stabilization, urban utility integration, and open space programming. The first stage of construction focused on complete site clearing and demolition of the former structures. This phase involved selective dismantling techniques to minimize dust and vibrations, as the site is located near active traffic corridors, office buildings, and riverwalk segments. Demolition debris was sorted and recycled as part of a broader sustainability mandate, and existing below-grade utilities were mapped, capped, or rerouted to prepare the site for redevelopment. With demolition complete, the site was surveyed in high resolution to inform the grading and drainage plans. Given its proximity to the river and its susceptibility to tidal fluctuations and storm surges, the grading plan called for subtle terracing and the integration of bioswales to manage stormwater naturally. Fill material was imported and compacted in lifts, each tested for density and moisture content to prevent future settlement. Geotextile membranes were installed between fill layers to enhance soil stability and prevent erosion along the river's edge. One of the central challenges of the Riverfront Plaza redevelopment was the construction of structural retaining elements and hardscape features capable of withstanding both pedestrian use and hydrodynamic forces. Reinforced concrete retaining walls were formed along the Riverwalk edge, designed with weep holes and subdrain systems to relieve hydrostatic pressure. These walls were anchored into the subgrade with helical piles in areas with softer soils, ensuring long-term stability against the variable forces of tidal surge and river currents. The plaza itself was constructed using a combination of cast-in-place and precast concrete paving systems, arranged in geometric patterns and supported by a subbase of compacted aggregate and fine leveling sand. Embedded conduits and utility chases were integrated beneath the hardscape to support lighting, irrigation, and security systems. Special attention was given to expansion joints and surface drainage in the plaza design, with trench drains and permeable surfaces used to quickly shed water and avoid pooling during heavy rains. To support programming flexibility, the site included several utility stub-outs and foundational footings for potential future vertical structures such as pavilions or public art installations. Electrical cabinets and water connections were recessed and weatherproofed, and fiber optic conduits were installed for surveillance and wireless communication infrastructure. Landscape elements, including native trees, shrubs, and grasses, were selected for salt tolerance and deep root structures to minimize wind throw during storms. Tree pits were designed with structural soils and root barriers to protect adjacent pavement. Lighting was provided through architectural-grade LED fixtures mounted on concrete bases or embedded in pathways for both aesthetic and functional illumination. But just wait until you hear about the Cornell Tech Campus, a revolutionary research hub on Roosevelt Island, New York, that is transforming the future of education and sustainability. This campus is a hub for cutting-edge research in artificial intelligence, cybersecurity, and robotics, making it a key player in the global innovation ecosystem. Cornell Tech was first announced in 2011 when Cornell University and Technion Israel Institute of Technology won a highly competitive bid to build a new technology-focused graduate campus in New York City. The vision behind the project was to create a world-class institution that would drive economic growth and foster innovation in fields such as AI, data science, and digital security. Construction of the campus officially began in 2014, with the first phase opening in 2017. Since then, Cornell Tech has continued to expand, adding state-of-the-art facilities, sustainable buildings, and cutting-edge research centers. The Cornell Tech campus is designed with a focus on sustainability, innovation, and digital connectivity. The campus includes several groundbreaking structures, such as the Bloomberg Center, the Tata Innovation Center, and the House, each serving a unique purpose in academia, business, and residential life. The Bloomberg Center, named after former New York City Mayor Michael Bloomberg, is a zero-emission building powered entirely by solar panels and geothermal energy. It features smart classrooms, AI-driven labs, and open collaboration spaces, promoting interaction between students, researchers, and industry professionals. The House, a residential tower for students and faculty, is the first high-rise, passive house of the world. Built with extreme energy efficiency in mind, it reduces energy consumption by nearly 70% compared to conventional buildings. The double-insulated windows, airtight construction, and advanced ventilation systems ensure maximum efficiency and comfort for residents. The Cornell Tech campus has a budget of over $2 billion, making it one of the most expensive educational infrastructure projects in the United States. The modular construction approach has played a key role in reducing costs and accelerating development. Prefabricated building components were assembled off-site and transported to Roosevelt Island, reducing construction waste and energy consumption. The project employs advanced robotics for precision construction, as well as autonomous cranes and AI-powered monitoring systems to enhance safety and efficiency. The use of geothermal wells, smart grid technology, and photovoltaic panels allows the campus to operate with near-zero emissions, making it one of the most sustainable academic institutions in the world. The first phase of Cornell Tech campus was completed in 2017, while the second phase is scheduled for completion in 2027. By 2037, the full campus is expected to span 12 acres. But we have to talk about one of the most expensive mega projects ever constructed in Saudi Arabia. The King Abdullah Economic City is designed to diversify the national oil-dependent economy and position the country as a global investment hub. Announced in 2005 by the late King Abdullah bin Abdulaziz, King Abdullah Economic City spans a staggering 173 square kilometers along the Red Sea coast in the Rabigh Governorate, Mecca province. Located 100 kilometers north of Jeddah, King Abdullah Economic City boasts strategic proximity to major cities like Mecca and Medina, making it an essential piece of the national developmental puzzle. King Abdullah Economic City was part of the 10x10 program in Saudi Arabia, aimed at placing the country among the top 10 global investment destinations by 2010. It was envisioned as a self-sustained city featuring residential zones, industrial parks, and a state-of-the-art seaport. Planned to be completed by 2020, King Abdullah Economic City aimed to create 1 million jobs and house a population of 2 million. However, progress has been slower than anticipated, and by 2018, the city housed just 7,000 residents. The crown jewel of King Abdullah Economic City is the King Abdullah Port, a vital node in the maritime Silk Road connecting China to Europe via the Suez Canal. This world-class port aims to become a logistics hub for the region, with capabilities to handle millions of containers annually. The city also features cutting-edge residential areas like Bela Sun Village and Esmeralda Suburb, along with plans for educational institutions such as Columbia University and Thunderbird University. King Abdullah University of Science and Technology, located 20 kilometers from King Abdullah Economic City in Thual, is another major highlight. Opened in 2009, it serves as a hub for scientific research and innovation. Built by MR Properties, the estimated cost of King Abdullah Economic City is $95 billion. Construction employs a mix of modern techniques, including modular systems for residential zones and cutting-edge logistics infrastructure at the port. The city also integrates smart technologies to support sustainability and efficiency. King Abdullah Economic City is served by the Al Haramain high-speed railway, linking it to Mecca, Medina, and Jeddah. Inaugurated in 2018, the railway ensures seamless connectivity for residents and visitors, further enhancing the appeal of the city. Despite its grand vision, King Abdullah Economic City has faced criticism for falling short of its initial goals. The Financial Times described it as a cautionary tale for over-ambitious projects in the region.
We can't overlook the massive Klamath River project. With a price tag of $450 million, this project involves removing 4 hydroelectric dams to restore natural fish migration patterns and improve water quality. For over a century, these dams have blocked vital fish habitats, and the removal is set to be completed by the end of 2024. This will open up 400 miles of river for species like Chinook salmon and steelhead trout. Let's dive into the engineering behind this transformative project. The 4 dams planned for removal are known as the Lower Klamath Project. They include the J.C. Boyle, Copco No. 1, Copco No. 2, and Iron Gate dams. These dams were originally built for hydroelectric power generation, but they've also severely disrupted natural water flow and fish migration for decades. So how do you remove dams that stood for a century? At J.C. Boyle Dam, an existing drain that was originally built to divert water during the construction of the dam will be used to drain the reservoir. Concrete step logs currently blocking this drain will be blasted open to allow the water to flow through. Once the reservoir is drained, workers will begin demolishing the dam structure itself. Meanwhile, at Copco No. 1, engineers will drill a new tunnel through the base of the dam. This tunnel will act as a controlled release point for water. The demolition crews will use drilling and blasting techniques to dismantle Copco No. 2 and Iron Gate Dam. The goal of this project isn't just about removing dams, it's about restoring an entire ecosystem. The Klamath River Project is the largest dam removal project in U.S. history. It's part of a growing movement to rethink how we manage natural resources, prioritizing ecosystem health and sustainability over industrial infrastructure. Projects like this set a powerful example for future ecological restoration efforts. Over 76,000 cubic meters of concrete and 2,000 tons of steel will be removed. Nearly 1 million cubic meters of material will be excavated to return the river to its natural state.